Hello, everyone, and welcome to the latest podcast broadcast of This Week in Science. We are here again to talk about all the science we love to bring. And I do have to, as we start the show, just remind you this is the pre show before we get started. Everyone, tap your microphones. Make sure everyone can hear us in the comments. Woo woo! Comments, are you here? Are chatters here? You ready? You watching? You there? Whoop whoop. Okay, everyone. This is the place where you watch it live, This Week in Science. And if you would like to get the edited, technical difficulties taken out version, then make sure you subscribe to the podcast because that is where that is. Subscribe to the podcast anyway. But right now, like, subscribe, share, do all the things, get us in the algorithms because it is time for us to go live. Oh, yeah, we were already live, but we're starting the show now. Okay, beginning the show in 3, 2. This is TWIS. This Week in Science, episode number 990, recorded on Wednesday, October 16th, 2024. Some JWSTful thinking about the universe. Hey everyone, I'm Dr. Kiki, and tonight on the show, we will fill your head with meteorite bits, lion bites, and everything but the bang. But first.
Disclaimer. When Einstein formulated the field equations describing properties of spacetime, no one could have predicted how much we would learn from it. Equations on paper, illustrating that matter tells spacetime how to curve, and curved spacetime tells matter how to move. Gravitation arising not as a propagating force, but rather as a feature of spacetime itself. The weight of objects on Earth, your own weight, due to your body traveling through warped spacetime. The predictions that fell like loose crumbs from these equations: gravitational lensing, gravitational redshift, gravitational waves, black holes, time dilation, frame dragging, and dynamic spacetime either expanding or contracting, the equivalence principle, even the cosmic microwave background distribution were predicted as consequences of Einstein's work, and all have been confirmed. At a time when the known universe was just the Milky Way galaxy, a universe trillions of times larger was fundamentally figured out. And while we don't have all the answers yet, we do have a great place to start asking those questions. Right here on This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science to you, Kiki.
And a good science to you too, Justin, and everyone out there. Welcome to another episode of This Week in Science. We are back again to talk about all the science from the last week. And oh my gosh, tonight we have an interview with the amazing Dr. Ethan Siegel, who's here to discuss
Hi,
his
everyone.
new book.
Thanks for having me.
Yeah, thanks for
welcome
joining us. Welcome to the show.
My pleasure to be back.
I hope that we will talk about a few astrophysics-y things this evening.
You know, I've been prepped, and even from his intro, I bet you Justin has no shortage of questions for me.
Oh, yes. Yes. I've tried. There's a whole cosmos out there, and I understand none of it.
It is. Let's go to school with Dr. Siegel.
Ooh, it's been a little while since I was a college professor, but, you know, I'm happy to share with you all that we know. Just no equations, no exams. Just enjoy yourselves.
Best kind of school there is.
Yeah, and that is a wonderful way to start this show. All right, everyone. I have stories tonight about a clipper ship, which I think Ethan will be able to weigh on as well. Some lion snacks, not lion, mouse noises, and elephant wrinkles. What do you have for us, Justin?
Oh, what have I got? I've got the origin of almost all meteorites has been figured out. A
The One
secret
Ring.
tomb beneath one of the new 7 wonders of the world, Petra, has been located, discovered. And what else? I got one more. Is the dental industry a scam? An ongoing conversation from
It is.
internal medicine.
I think that we've had some of this conversation as well historically.
I think I've ranted about it in the past.
have
This
ranted,
one is
so
now the rant
see where
has
this goes.
spilled over into letters and viewpoints on JAMA internal medicine, and it's a little bit revealing.
All right. We'll get the inside scoop on the dental industry. But right now, it's time to get started with the show. But before we do, I just want to remind you all that we stream live Wednesday evenings, night, morning, wherever it is. 8 p.m. Pacific time is where we start the show-ish. And that's on Facebook, Twitch, and YouTube. You can find us by looking for This Week in Science. TWIS Science is where you find us. TWIS, you can look for these things. Also, our podcast, you can subscribe to us. And you can find all this information and a lot of show notes and fun stuff at our website, TWIS.org. Okay, time to jump into the show. Okay, so first off, the starting line tonight. This last week, SpaceX launched a super heavy rocket, and every time it's a super heavy rocket. It's a big one, gets it out there because it's launching the Europa Clipper out away from the Earth. It's a whole lots of force, get stuff out away from the planet. Need more big to get more far. This is breaking down orbital dynamics and space travel just to its most simplistic form. See, I good science communicate. Anyhow, yes, I do, just as a total complete aside, because I have been tangential thinking recently. Every time we have Starship, I think of the Lego movie and the little Lego character who goes, spaceship! And so I run around the house going, Starship! And so this last week with the Super Heavy, I know it wasn't the Starship, but at the same time, I was running around the house going, spaceship! So anyway, I get excited. It's a whole thing. This launch put on its journey the Europa Clipper mission. The Europa Clipper mission is set to head to Europa, which is a moon of what planet in our solar system? Test time.
Jupiter.
You're in school. Ethan, you're like counting it down. Europa is one of the many moons of Jupiter. That's right. It's one of the many moons of Jupiter, and Europa is special because it has an icy crust. But beneath that icy surface, it may have a liquid. We know it has a lot of liquid under there, but a liquid ocean of carbon-based materials. So methane, ethane, stuff that doesn't freeze at the temperatures that you would experience on a moon of Jupiter, which here on our planet, we don't get anywhere near that cold. So these things are gases, but around Jupiter, they're liquid. It's pretty amazing. Anyway, why are we interested in that? Well, because geophysical forces around this moon and the magnetic forces from Jupiter itself might actually be crunking and crushing the inside and the outside of Europa to make it kind of habitable, possibly. There are these vapor sprays that come out, lots of bubbles and neat things. And what could possibly be interesting there? Maybe life. And so this Clipper mission is headed to Europa to search for signs of life. And Ethan, you wrote up a really big, wonderful report on the Clipper mission on your Starts with a Bang blog. Also, the big, a big think, or Big Think is the main website. And you might have to unmute your microphone.
All right. Well, you want to hear a little bit about this? So the Clipper mission, this is launched just this past week, just 2 days ago. It's actually going to take 5.5 years to get to Jupiter, because its first stop is going to be to fly by the planet Mars in March or April of next year. And that's going to send it back towards Earth, and it's going to pass by us again in late 2026. And those two combinations of flying by Mars and flying by Earth is going to give it enough of a gravity assist that it can make it all the way to Jupiter, where it's going to interact with Jupiter and its moons to be gravitationally captured. Now, Jupiter, like you were saying, has an enormous amount of radiation that it gives off, right? It's strongly electromagnetic. It emits radiation from its cloud tops. If we had the Europa Clipper mission just orbiting around Europa, it's so close to Jupiter that the radiation from Jupiter would kill it within months. We don't want that. So what we're doing instead is we're saying, well, this Clipper is going to be really far away from Jupiter for most of the time, and then it's just going to dive in and fly by Europa and then go right back on out. And this is going to give it a lifetime of closer to 4 years. So it's going to be able to do more than 40 close flybys of Europa, including flybys as close as 25 kilometers off the surface, which is only about 15, 16 miles. So wow, we're going to get the closest, highest resolution images of Europa's surface. We also have a suite of instruments on board where the Clipper mission is going to be able to do radar ranging. It's going to determine if there are any thin spots in that icy crust. It's going to see if there's recent or even current activity of ejection of plumes from Europa. And it's possible that it may even fly through some water that's shooting up from the planet's surface. We know this happens around Saturn's Enceladus. It may also happen around Jupiter's Europa. We're going to find out. We know already it has a crust of ice. Is it a thin crust or a thick crust? How deep does the ocean go? Is it a thin subsurface ocean or a thick subsurface ocean? And importantly, does the ice crust on Europa, is it just a shell that floats and migrates around the whole planet? We know, we discovered back on Earth in the 1970s that way down at the bottom of the ocean, where we have volcanic vents, where Earth's mantle is maybe only a couple of miles under the surface, these vents are teeming with life. This is extremophile life. Could something similar be down there on these ice worlds in the solar system? Europa, Enceladus, Neptune's moon Triton, Pluto, maybe Eris, maybe some other Kuiper Belt objects? We don't know. Flying the Europa Clipper mission, that's the NASA mission. The ESA is doing their own version. It launched last year, and it will arrive at Jupiter in 2031, 1 year after our Europa Clipper mission gets there, called JUICE. So between Europa Clipper and JUICE, we're going to get enough information about Europa that will tell us, is it like we think? Is there the possibility of life? Are there possible hints of biological activity that we're seeing? This mission is going to be a huge, huge boon to planetary science, because remember, when we're looking for life elsewhere in the universe, we're not just listening for intelligent extraterrestrials, and we're not just looking at exoplanets around other stars and seeing, are there biosignatures there? Yeah. We have our own cosmic backyard with not just Earth, but Venus, Mars, and a whole slew of moons around the gas giants, plus dwarf planets and more. The possibilities for life are extreme. Most of it isn't going to be as complicated or differentiated as we are, but it's still interesting. Remember, we've never yet discovered life that originated anywhere other than planet Earth. This mission to Europa could give us the clues we need to find that with the next generation of missions.
I think that is like one of the biggest stepping stones is, okay, we think we have what we understand about the building blocks of life. We think we see these signatures. There are things that suggest this is a possibility. Okay, we got to go there. We have to go. We have to check it out. Is there anything that, I mean, what would we find that would just be like, okay, there's no life? Like, is there anything that would be like okay, null result, like nothing is happening
I
there?
mean, we could be really
Vanilla.
surprised, right? We could find that this shell is a hard shell. We could find that there's no interface between the water and the outer stuff. We could find that, unlike Jupiter's moon Io, which experiences tides that are so strong it actually tears the planet apart, it's the most eruptive world in the entire known universe right now. Europa, we think, should be getting a bunch of that tidal heating too, but dependent on the size of its core, we could be all wrong about that. So there are certain things we could find. They'd all be surprises that tell us it's not inhabited. But what I'm really interested in is this possibility that there is something interesting down there, and that when we measure the gases coming up from Europa, maybe we'll actually see, ooh, there are some molecules in there I didn't expect to be in there. And what does that mean? Because ideally, someday we'll be able to not just land on Europa, but send a probe down through the icy crust and probe those salty waters underneath. Is there life in there? Is it life that's completely unlike anything we recognize on Earth? Does it use different amino acids? Does it encode information with DNA, or does it use a different type of molecule? We don't know any of this, but this big question of how life first arose from non-life, wow, if we had a second example of that happening in our solar system, unrelated to what happened here on Earth, that would be profound, and it would change everything as far as our understanding of life in the universe.
And why not have it be someplace else here in our own solar system, which we know is already a great place for life, at least on this planet?
Yeah, I mean, we think Mars had it in the past. Maybe even Venus had it in the past. Why not look under the ice? Follow the water, right?
Yeah. And that's I think one of the things also, the universal solvent, water. It's frozen. Mostly it's going to be fairly frozen on Europa, but we
Well, but
have
that's the
other
great thing,
solvents,
right?
and then
Is you
there's
get pressure. You get pressure, and even a frozen thing, if you apply enough pressure and it's water, it's going to turn into liquid. So liquid water, nice
V equals nRT.
polar environment for all your salts to dissolve in.
Yeah. Absolutely. And as we're finding even here on our own planet, water is incorporated into many minerals and many mixtures beneath the surface of our own planet that we didn't expect to find it in. And so that has allowed a lot of understanding of chemistry as we look at Mars and as we look at other places where it's not liquid water necessarily, but the water is there. It's allowed us to look at the moon with an eye for habitation by humans in the future. So there are all sorts of ways to look at the potential for whether life could exist, does exist. And
if you want a real dark horse of where to look for life, I recommend not Jupiter's first moon Io or its second moon Europa, but its third moon, Ganymede. Ganymede is the largest moon in the solar system. It also has more water than any other solid-bodied world in the solar system. It has something like 30 times as much water as the entire planet Earth does. You look down at Ganymede, it turns out if you go under the surface, we think down there under the solid surface, there should be liquid water once you get to enough pressure too, just flowing through whatever type of soil is down there. And I don't know if you can have life exist in a subterranean environment like that.
Why
but
not?
If I were going to bet on that, I would say, you know what? Take a look at Ganymede. Maybe it'll surprise you.
Well, and take a look at the Earth, because the Earth has
surprises everywhere.
life forms well deep within the soil, even deep beneath the soil of the ocean. And when we talk about like looking for, a lot of the times there's a focus on, oh, we found Earth-like planets. Life didn't necessarily start on planet Earth anything like the Earth is today, right? So what the ideal starting point was, where we are as a planet and the evolution of life adapting to this changing planet might not be might not be the best case scenario for formation of life. We have no idea what that ideal condition even is. So maybe something protected underneath a giant ice sheet or deep beneath the soil is actually a better starting point for these things to start.
Especially with all of the
use your imagination, right?
Yeah.
There's a big cosmic lottery out there. We got a winning ticket here on Earth, but we don't know what the other prizes are out there, if we're even the grand prize, or what the odds of winning anything are. So,
and I like that you brought up the
I just want a participant ribbon.
a DNA with different nucleotides, because that was other possible ways that life could have formed. I think if we discover life, that one of the things that we will find is the building blocks would be likely very similar. And I think we will even see something that's like a double helix, because what the double helix is it's a structure that keeps things together. And so there could be other formations that exist, and single stranded and what have you. But for something that's a little bit more stable, that double helix just is the form that keeps things from pulling apart lengthwise or side to side. And so it's very likely that we'll even see something that looks similar to what we experienced here on Earth. So yeah, I think I'm very excited about this mission. I gotta wait, what though, 9 years to get these results? Gosh.
You gotta wait 4.5 years for it to first get to Europa.
Space travel is so slow.
Well, space is pretty big, and what Kiki was telling us earlier about big rockets, no matter how big your rocket gets, unless you're not going to use chemical-based fuel and you're going to switch to like antimatter fuel, which we don't really have that technology yet.
Don't have that yet. Nah.
Unless you're going to do that, you really best bet is to get your big gravity assist from other planets to boost you to where you want to go. But because you have to play this game of cosmic billiards with the masses in our solar system, you've just got to wait for gravity to do its thing. And unfortunately, it takes a little while for a spacecraft under the solar system's gravity to make it from Earth eventually all the way to Jupiter, because you don't want to send it as fast as possible. You want it to go up to Jupiter just almost moving at the same speed as Jupiter.
Yeah.
So that it has to have that insertion velocity, right? Where it basically is like, oh, I'm just with you now. It get captured by the gravitational.
If you've ever played Kerbal Space Program, you want to get your delta V's just right.
Yeah.
Well, there's no brakes.
Kerbal Space Program.
There's no space brakes. Hey, if you get going too quick, you're just gonna zip on by. You have to turn around.
That's what New Horizons did, right? New Horizons said, "Hey, guess what? I'm going to get to Pluto, and it's going to take me less than a decade," and it did. And now it's like 1 billion miles from Pluto. It flew past it once, and that was it.
And it keeps going, and it's so exciting. I love all of it.
It's amazing, but also
well planned.
I don't want one flyby of Europa with this mission. I want those 40 to 50 flybys. I want to get all that good data.
Well, it's like what they've learned a lot of lessons from the Juno mission at Jupiter, because they have discovered that they're able to create a craft that can withstand all of those electromagnetic forces, gravitational forces of that giant planet. It has been collecting data much, much longer than they expected us to. So good job, engineers. You did the thing. It's amazing.
And
so
for everyone worried,
that,
what about Clipper mission? Guess what? They put the strongest radiation shield ever put on an automated spacecraft on the Europa Clipper mission. So it should really make it at least 3, possibly even close to 4 years before
Excellent.
that radiation from Jupiter finally puts it out of commission. But I
Tries their
never bet
electronics.
against NASA engineers when it comes to over-engineering something that's headed to another planet.
Yeah, this has been
Speaking
been the pattern, because it's when you said 4 years, I immediately thought 6 to 8 at least. Like, if they're saying 4, they've been under promising and over delivering on these missions. So,
but the time of the travel is it's the time of the travel. So we've got until what, 2030, 2031 before we see any data. So fingers crossed. But I will be looking forward to information from Mars as it passes by Mars for that slingshot. I'll be looking forward to its pass by Earth, because NASA is going to be telling us other things about the billiards game, because it's a long-term game. And speaking of billiards, once upon a time, something played billiards in our solar system, and now there's a bunch of meteorites on our planet. Justin, do you want to talk about them?
So this is an international team of scientists has determined that approximately 70% of all known meteorite falls originate from 3 young asteroid families located in the main asteroid belt. These are the asteroid families of Charon, Coronis, and Massalia. What's interesting is these asteroid belts were formed very recently, cosmologically speaking. It says the collisions took place 5.8, 7.5, and around 40 million years ago, meaning that these asteroid families, where most meteorites that we've found originate from, all kind of got their start after the age of the dinosaurs. So this is somewhat recent material that's falling. The findings published in 3 scientific papers reveal that the Massalia family alone accounts for 37% of all known meteorites. Prior to this study, only about 6% of meteorites had kind of origins identified. Large ones, some that included things from Mars and even the moon. So when this new research, they have actually identified successfully sources of more than 90% of the known meteorites, which is still intriguing, because that means that there's 10% that they have looked at that they could not determine a specific origin. Part of that, of course, is you have to have had some sampling that allows you to determine where that is in connection. So the study explains that younger asteroid families contain higher numbers of small fragments resulting from recent collisions. So part of the reason that we're seeing so much of our meteorites coming from younger asteroid belt formations is because their crashes were more recent, so the gravity hasn't had as long to sort of take out all the debris, right? Either combining from gravity out there, or already has flung off and gone somewhere. So part of what the reason we're seeing them as younger is because that's what is still loose and floating around. Solar system has a way.
It's kind of cool, isn't it? This happens all over the solar system too, not just in the asteroid belt. Like, take a look at Saturn, right? And you think, oh, Saturn, that's the one with the giant rings. Guess what? The more we study them, the younger we learn that Saturn's rings are. Saturn's rings could have been created no later than 150 million years ago, which means for over 4 billion years in the solar system, Saturn probably didn't have those rings. What happened is instead it had a moon that likely got destroyed either by tidal interactions or by a giant collision, and some of that debris got stretched out into a ring that now is mostly water. That's mostly what's left is water ice. Saturn's rings, 99.9% water ice. So I'm not surprised to learn that, we have a bunch of asteroids that landed on Earth. Oh no, is the cosmos trying to kill us? No, the stuff that would have been trying to kill us mostly got cleared out after the first few 100 million years of the solar system. And it's really only either gravitational interactions or collisions that randomly send up this debris. And it's no surprise that accounts for the majority of meteorites that have fallen on Earth. In fact, when you look at the ones that came from Mars, those correspond to just a few specific, we know this was created this many millions of years ago, and this was created this many millions of years ago, and they fall into those families. Why? Because likely Mars got smacked by something big, it kicked up some debris, and a little bit of that debris migrated over to Earth, didn't burn up in the atmosphere, and landed on the ground. And you can buy a little piece of it from meteorite collectors all over the world.
Yeah, I've always played with the idea that we could find dinosaur fossils on the moon. Right? We got smacked. We got smacked pretty hard.
A really big impact, and it's pretty difficult to get stuff off of Earth through the atmosphere. But you know what? We know it happened at least once because we have a moon, and the only way you make a moon like that is with a giant impact itself. So it happened once.
It happened once. But we don't have two moons. We only have one moon. So we are going to guess that there was only the one big impact.
I'll blame it on that. Mars has two moons. We think it once had three, and that its big one fell back to Mars a long time ago. But that is still speculative.
Right. So, I mean, we've possibly have had a ring around Earth. That's a new hypothesis. Saturn has had its rings come and go. The dinosaurs, they're not on the moon. I'm just gonna put it out there. Likelihood of dinosaurs being launched onto the moon, very, very, very low. Likelihood of dinosaurs having been, the moon's been around longer than the dinosaurs. So
this is true.
So
the dinosaurs had the same moon to look up at as we do. Their moon was just a little bit closer. It's moved a little bit farther away since the time of the dinosaurs.
So it was a little tiny bit bigger in the sky. Their super moons were a little more super.
More total solar eclipses for dinosaurs, fewer annular solar eclipses for dinosaurs.
Good. That's an interesting little bit of trivia right there. Okay, people who write trivia questions, take that one. Okay, but with this information about the meteorites, like what are we finding out about these different populations, and what can we say concretely about how old they are, where they came from, what made them hit our planet?
Well, the big thing you look at when you have these collisions, right, is you say, okay, we have these collection of objects. What are their mineral properties? But also, you have radioactive dating. When something was created based on, if you get hit with, solar wind or cosmic rays from the sun, you get, certain properties that are going to get frozen into you at the moment of your creation. And then, bam, when something smashes into you and breaks you apart, you have whatever elemental abundance, whatever relative elemental abundance was in you at the moment of your creation. So you can look at things like the relative abundance of the elements inside of these objects, and that tells you when did a recent event occur? When did a cataclysm occur? And so that's how we can date the meteorites that come from Mars, or the meteorites that come from the moon, or, as this new research shows, the meteorites that come from these various families of asteroids. So you learn something about, we're not just saying like, this is a stony iron meteorite and this is a nickel iron meteorite. We can classify these things much more granularly now than we could back when we were first like, hey, that rock looks weird. What do you think? Just bury it with the others. No, we're being real careful about this. Geology, planetary science, this is a real robust scientific field now. And the fact that we've gone in, one generation, we've gone from, we've classified fewer than 10% of the meteorites we found to we have fewer than 10% left of meteorites that still need to be classified. That's a huge leap. That we've gone from less than 10% to more than 90%.
Yeah. That's a massive leap. So suddenly we're able to go, hey, something big hit something big. There were pieces that got thrown off and they went beep, choo, choo, and we are now
more
able to.
accurately, something hit something big, and then the big thing wasn't a big thing anymore. It was a lot of small things, and some of them came our way.
Yeah, what I find interesting, and it's not really the visualization in the figures in these papers don't really show off the kind of time rewind, right? Which I would love to see somebody take a supercomputer from a national lab and create a visualization of, okay, what happened? If you had a big thing hitting and we know from where we are now, where we were, how many years ago, and basically they logically stepped through all of that information. But it would be so neat to be able to visualize that.
You have to do certain things beyond like, okay, I'm just going to calculate and throw it into my gravity simulator, because after a few 100,000 orbits, your simulation resolution starts to be a little bit of a problem. The universe itself doesn't have a problem doing that. We don't have any problem with the universe saying like, no, we're just going to keep orbiting just like this. But you put it in a simulator, that's still something that, I don't know how many chat GPTs it takes to get that right, but that's not where we are just yet.
That's not where we are. No, I don't know. I feel like being able to rewind and get an idea of how things actually worked. I mean, the moon was closer to our planet. It's further away now. How have our orbits changed? There's, conversations about the outer planets having come in closer to the sun at various times, and how did different movements of different planets in the orbits around the sun impact the way that this billiard game has taken place. That's
a tragedy of coming along so late in the game. Yeah. Is here in our solar system 4.5 billion years after the creation of the Earth. All we have left are the survivors. We don't know how many we started with. We don't know how many were there initially. Were there more than 8 planets in our solar system at one point? Were there 9, 10, 11? How many were there? Were they gobbled up? Were they hurled into the sun? Were they ejected out of the solar system? Were they wander the universe as rogue planets? Did we send some poor forgotten planets from our antiquity into, like, did we just orphan them and say, you're out of here, goodbye? We have no idea, but this happens in the universe, and all we can say is we're one of the survivors.
Justin, did you have any more thoughts on the survivors of this meteoric story?
No, but I think you guys hit all the key and interesting parts there.
All right, well, I'm going to take a quick moment now just to say that this is This Week in Science. Thank you, everyone, for watching the show. We are so glad that you are here, or maybe listening to the show. Are you listening as a podcast? I hope you are. If you are and you like it, please share TWIS with a friend today. I mean, come on. More science, more sharing of science means more happy people in the world. So let's do that. Additionally, you can head over to twis.org. And if you would like to support the show, click on our Zazzle link or our Patreon link. That will take you to websites where you can either become an ongoing supporter of the show, Patreon, or where you can purchase merchandise like hats and mouse pads and other fun things, and support the show by purchasing some of the things that have the TWIS logo on it. But anyway, just you being here, really, really, it helps a lot. So thank you for being a part of the show. Thank you for supporting us. And we really can't do it without you. All right, we're going to come back again now with the official interview with our guest, Dr. Ethan Siegel. And
put my official hat on.
Yes, now it's official. Okay, so officially, let me introduce you to those people who may not know you. Ethan is a theoretical physicist and science communicator, writer and host of Starts with a Bang. You might have seen his work on Big Think or on his Medium. Was it a website or anyway, the Medium platform, or also on startswithabang.com, which is the website where a lot of information about Ethan can be found. Ethan has written some books, Technology, one of my favorites. But right now, Ethan is celebrating the publication of a new book on the inside story behind the James Webb Space Telescope, or as we like to call it, JWST, with National Geographic. And so many pretty pictures on the inside of it, and also a foreword by physicist Brian Greene. It's super cool. It's called Infinite Cosmos. And oh my gosh, Ethan, thank you for joining us tonight.
Oh my goodness. Thank you for having me on. This was an absolute dream to get to write. I have been a huge fan of the James Webb Space Telescope since over a decade before it was launched. As soon as I learned about NASA's great observatories, that it wasn't just Hubble, that it had Spitzer and Compton and Chandra, and then I learned, like, oh my goodness, like, you can build space telescopes to probe almost any wavelength of light if you get more precise in any wavelength range that we haven't looked precisely at before. Bigger telescopes, higher resolution, more light gathering power, supremely optimized instruments. The limits to what you can discover, you don't even know what they are. The best part for me about the James Webb Space Telescope and why I was so excited about it from its inception is that it has what I think of as discovery potential. Yeah, we're going to build it and we're going to optimize it for a whole bunch of things that are no-brainers, right? Oh, we're looking in long wavelengths of light. Let's find that light emitted by the most distant galaxies that got stretched by the expansion of the universe to these long infrared wavelengths. Imagine that you've got something like these young hot blue stars, they're emitting ultraviolet light that you can't see, and the expansion of the universe stretches that light so it becomes visible, goes from violet through red, then becomes infrared and gets stretched so long you need to build a James Webb Space Telescope to see it. So yeah, we knew we were going to find the most distant galaxy and break the old record. We knew we were going to find the earliest galaxy clusters, the earliest supermassive black holes, the most distant gravitational lenses, the most distant individual stars we've ever seen. In its first 2 years of science operations, James Webb Space Telescope, or JWST, has broken all of those records. But to me, that's not even the most exciting part. The most exciting part is the stuff that it didn't even know it was going to find. Is the stuff that we said, hey, it's optimized with these capabilities. Let's go look in these places and see what you can find. So we said, okay, let's take a look at the Orion Nebula, the closest star-forming region, the big, massive one to Earth. What do we find? It's 1,300 light years away. Yeah, we knew we were going to see gas and dust and fainter stars and protostars with protostellar disks that are still forming around them. We knew we were going to get them in more detail than we've ever seen before. What we didn't know we were going to find is, in addition to all the stars we're finding, there are these Jupiter mass and super Jupiter mass planets that never even got massive enough to become brown dwarfs. But James Webb Space Telescope is so sensitive to these long wavelengths of light that it can see these Jupiter-like planets shining from over 1,000 light years away, just shining with their own infrared radiation that they emit from gravitationally contracting. Imagine if you had eyes that could see that you could see Jupiter shining like a second sun in our night sky. That's what James Webb Space Telescope can do from over 1,000 light years away. Unbelievably, these parentless planets that found, 9% of them are twins, or at least brother-sister. They orbit together in binary pairs. We didn't even know to expect that. We called them jumbos. Here's a fun thing that I love that the James Webb Space Telescope discovered. Imagine you came and you looked at Earth in the early days of the solar system and you said, oh yeah, it's one of those little protoplanets, right? You get a star, you get some planets, you get an asteroid belt, you get more planets, and then you get a Kuiper belt. That's what a solar system looks like, we thought, right? No, that's what our solar system looks like. With the James Webb Space Telescope, we got to look at a second one, the closest stellar system to us that still has a debris disk around it is the Fomalhaut system. We took a look with the James Webb Space Telescope, and yeah, we found a disk that we think has the analog of the asteroid belt. And yeah, we found a ring that we think has the analog of our Kuiper belt. But in between them, we found a third belt. We found an intermediate belt. Now, we don't even know, is our solar system typical? Is the Fomalhaut system typical? Is a different number of belts typical? We don't even know. We assumed that things were like us. And now, we don't even know if we're in the realm. Are we common? Are we uncommon? Are we rare? What is the most common? These are the types of things that really get me excited, where I'm like, we didn't even know to look for that. But because we built a thing that was capable of discovering what was out there, we were able to make these discoveries and blow our own minds.
So that's one of the things that I think is really exciting is the when science is like, hey, we plan to do this one thing, and then oh, look at this other thing. Now we're going to go down that rabbit hole. That was, we didn't even know that was going to be a thing. And now we have so many more questions. Like, so that to me is one of like the best parts of science. And so, you know, I've been thrilled about JWST for decades, and literally it has been decades, waiting for it to get launched and everything that was going on. So, I mean, from what you're saying, it is performing superiorly to what was expected. I mean,
this is one of the most remarkable stories to me is when you watch the Netflix documentary on the James Webb Space Telescope. Great documentary, by the way. I watched that first episode. I couldn't believe how depressed I was coming away from it, because it just talks in depth about the funding problems and the cost overruns and the mismanagement and the things that went wrong and the delay and the delay and the delay, and they found this error that they didn't think would be there. And I think to myself, you know what? That's not a bad thing. That's everyone working on it, being careful and checking and finding, oh, that shouldn't be like that. We're not going to let that slide, and catching everything, every little detail. And they super did. They had hundreds of points of failure, of possible failure that they had to guard against. And if anything didn't look perfect, they were like, no, you're going to fix this. You're going to fix this, and you're going to get it right. Because once that telescope gets on that ship, goes to the launch site, gets married to the rocket, and gets launched, there's no second chance. This is a one shot, all your eggs in one basket type of thing.
And whereas like Hubble, we can, it's close enough to the planet that we can send space shuttle, you know, not shuttle, oh my gosh, I'm so old. We can send space
It was the
station.
shuttle initially. We sent 4 shuttle missions up there.
Yeah.
That's right. We did. We launched
repairs.
it on a space shuttle, and we sent 4 shuttle missions up there to go service that thing. Because when we said, oh, its mirror is wonky, or, oh, Hubble was built for upgradability, it's just in low Earth orbit. But James Webb Space Telescope couldn't do that. We want this infrared observatory. We want sensitivity to these long wavelengths of light. And that means you have to be cold, way colder than you could ever get, having a hot planet like Earth just a few hundred kilometers away from you. Yeah, we're the ones who make it hot. We know that. Not you, son. It's us.
It's us. That's
but
right.
We know that, hey, if I get really far away and I put up a sun shield of reflective layer after reflective layer, I can passively cool my observatory, the optics, the instruments, the electronics, down to about 40 Kelvin. That's what that novel 5-layer sun shield with the James Webb Space Telescope successfully does, is it takes something that's in direct sunlight and it makes the cold side about 40 Kelvin. Then it says, well, I want to go even colder for my mid-infrared instrument. So they say, no problem. Bring a little liquid helium cryo cooler on board. We'll make a custom one, and it'll cool this instrument down till it's just 6 Kelvin. And there we go. We've got the coldest consistent observatory ever built.
And we're able to get these infrared pictures, but there's the near infrared camera, which is able to, see through the hot stuff in the universe so that we can actually get through the dust and the gas and see into places that we haven't been able to see before. But when we talk about like what is seeing things and what they're seeing versus like these pretty pictures that come back, that have been colorized and made gorgeous for, the average person to go ooh and ah about, like, what are the instruments that they are constrained by, and what are the measurements? Like, so there's, what are they measuring,
Right.
and
This is a
what
great
does that
question
tell
because
us?
this gets to how did we design this telescope and why?
Yeah.
So we have 4 instruments. You said we have the near infrared camera, we have a mid infrared camera, we have a near infrared spectrograph, and we also have the fine guidance system, which is essential for pointing the telescope as well as for many calibration options. So this allows us with NearCam, what we can do is we can start at about 600 nanometers of light. That's like yellowish colored light, yellow, orange, red. That's the end of the visible light. Then it goes all the way out to about 5 microns or 5,000 nanometers. That's what the near infrared camera can get you. That's about 250% longer wavelength than the maximum wavelength that Hubble is sensitive to. So just with near infrared eyes, with all these different filters, you can send the light through, say, oh, I want to know what's happening at 800 microns and what's happening at 1.5 microns and what's happening at 4.4 microns. And you can do that with all these different filters. We colorize these to say like, oh, we're going to assign red to you and blue to you and green to you. So we
shouldn't be talking about this because it's spoiler alert.
All those pretty pictures, yes, they've been colorized.
Some of that is a little bit of a signed artistry.
Well, you can say that. I will point out to you, I do have a whole section in this book about how we colorize these images. And I don't like this term false color that we've been using for a long time because we're not lying to you. We're trying to give you something that your brain's feeble, limited senses can interpret. You have these great eyes that are limited to this tiny, narrow range between 400 and 700 nanometers of light. I want to show you something that goes from 600 to 30,000 nanometers of light. Can you please let me just assign some colors to you so your feeble brain can understand what we're looking at? To say, okay, your eyes are going to see stars when you look with visible light. And if there's dust in there, you're hosed and it's going to block that light. But with the James Webb Space Telescope, you can see through the dust. Or you can look in the mid-infrared light and you can map out the dust, right? Maybe you only want to see things that are radiating at 150 Kelvin. Go ahead and use NearCam. It'll show you them. Maybe you want to see the really cold stuff that's only radiating at 25 Kelvin. Go look at the mid-infrared instrument. It's going to show you that. You've got a great picture up there now. This is the same object, these famous pillars of creation in the Eagle Nebula, taken with the James Webb Space Telescope in 2 different wavelengths of light. On the left, that you see on your screen, that is in mid-infrared light, and you can see the dust and the gas exquisitely, but very few stars. Meanwhile, on the right, you see different features highlighted in the dust because it's mostly the warm gas and not cold gas, but you can also see all the stars because they emit near-infrared light. So we're not cheating by showing you this. We're just giving you something your brain can digest, so you're not just looking at a blank piece of paper and being, oh, what an excellent mid-infrared interpretation for my eyes. No, you want to see it. So we're going to show you by colorizing the data, because all you have is rods and cones. It would be pretty bad if I didn't put that in a book for you.
A beautiful book.
Well, we apologize in advance for the pictures. They're all in deep infrared. Your eyes won't be able to actually see the images that we printed, but
But I mean, this is kind of like, genomic data is like a bunch of letters, or actually it's data, right? It's numbers. And so you don't want to look at all the numbers. Genomicists will look at the printout of the AATTGCGC, blah, blah, blah,
They
the letter.
don't look at that.
Yeah,
They
Actually,
don't,
but you're
they
not
don't
one
even
of those
look at
people
that. They
who have
run
all
it
64
through.
codons memorized for what amino acids they
right.
encode
But
or
but
stop.
anybody looking at stuff, it's more interesting to see a picture of, okay, this is the gene in this area, and this is what it integrates, and the pictures help a lot. And so they're not going to give us the massive data dump of numbers and stuff
And this
that
is
comes.
why most of the photos you'll see in the book are photos that were taken with an imaging camera as opposed to something that was taken with a
Oh.
spectrograph. A spectrograph is going to give you a tremendous amount of information, but it's not going to give you a
Thank
pretty
you.
picture.
Thank you for
And
that.
you can have the best of all worlds with something like the James Webb Space Telescope, because all of that raw data is where the valuable science is. That pretty picture that comes along with it, yeah, that's one way of representing or visualizing the data, but it's also something that even if you're a non-expert, you can see something fascinating. You can see something interesting. In fact, if you take a look, and this I'm actually excited to report was a discovery that came out after this book went to press.
There's always
There is a
going to be.
new cosmic record holder for the most distant galaxy. It is called Jade's GSZ14-0, and it is remarkable because you can see there's a very bright galaxy in the way. And it's just that there's a little bit of extra galaxy peeking out from it that you can see. This is a foreground galaxy that's much closer to us with a much more distant, fainter background galaxy. Oh, you've got a picture! Yes!
Of course I have
There
a
it is.
picture.
Jade's
So quick.
GSZ14-0 is the one with the little white arrow pointing to it. And the white thing next to the red thing is a closer foreground galaxy. You need to have instruments as good as the James Webb Space Telescope to be able to tell you that is not one weird looking galaxy. That is two galaxies, one that's close and one that's farther away, right on top of each other. The universe, as empty as it is kind of a crowded place still.
Okay, so I'm going to jump in here because I know that we're going to get right from this topic. We're going to bounce into all the stuff that Justin is interested in, which we're going to talk. I want to just start off with the conversation
This is one
about
of
the
them.
two.
This is one of them.
Yeah, this is the colors, okay? The
No.
red, and that, so when we're looking at these galaxies, you say red versus like white or maybe blue. Is there a reason that
there
you've
is
got
a
the
big reason for this? This is a
color?
good question. So how do you see a galaxy is really, really distant? The answer is, remember, you have stars of all types in all galaxies. They emit, when they're a young, hot, bright galaxy, it's going to emit mostly ultraviolet light. But that light has to travel through the expanding universe. So if my light starts out, my ultraviolet light, it starts out about 121 nanometers, and I don't see any ultraviolet light, and I don't see any visible light, and I don't see any infrared light at 800 nanometers or 1,000 nanometers or 1,200 nanometers, that I don't start to see something until 1,500 or 1,800 nanometers. That tells me all of those bluer wavelengths, they're not going to show up, because all that light has been stretched by the expanding universe, that there's no blue light left, no ultraviolet, no visible, not even that nearest infrared stuff. That's why that galaxy is colored red, because all of those bluer colors, the nearest infrared of the near infrared, the visible light stuff that's there for a closer galaxy like the white one you see in the center of the image. But that redder galaxy, the really more distant one, all of those shorter wavelengths of light have been wiped out. And that's how you can say, ooh, that's a really good galaxy candidate. I want to pull out my expensive near spec instrument and look at it take its spectra, and get for certain how far away is that puppy.
And this is the at least the second JADES galaxy that we've seen in this identified from this cluster of galaxies. The question, though,
at least the second, please. If you came to me 2.5 years ago, before the James Webb Space Telescope science operations began, and you said to me, hey, what's the most distant confirmed galaxy in the universe? I would have told you it's GNZ11 from a little more than 400 million years after the Big Bang. Then you say, okay, Ethan, now we're October 2024. Where is GNZ11? And I will tell you, it's not even in the top 10. It's number 11 on the list, because there are 10 galaxies either discovered or measured with JWST that are all more distant than them. I believe 4 or 5 of them are from the JADES survey. I'm fascinated because they found them in the GLASS survey and the SEERS survey and the Uncover survey, as well as the JADES survey. We have 4 different JWST deep surveys that have found galaxies that have broken the old Hubble cosmic distance record. But the biggest deep survey that JWST has done, Cosmos Web, they have not yet released their results. So there is a huge possibility that there is a record breaker that is out there, that has been imaged, that is just sitting in the data waiting to be released to the world.
And I think one of the things that's important about this is that just in JADES, and again, like you're saying, this is just the current oldest record keeper because we happen to spot it on the edge of this other four distant galaxy, right? This is the one we've captured that's currently the oldest, and there may be more coming. Already, this one is supposedly 390 something million years after the Big Bang.
285 million.
285.
That's the new record. 285.
Which is
how?
Like this is part of a galaxy
cosmic
cluster.
time machine, Kiki.
How?
It's part of a
farther away means farther back in time. You have a finite speed of light.
So the question though is, I thought our estimations of galaxy formation were supposed to be that galaxies show up a billion years or so after the Big Bang and can't have formed before. And here we are, closest we've ever gotten to our imaginary start point, or our, a placeholder start point for the cosmos. And we have galaxy clusters and galaxies already formed and already looking like pretty advanced.
Let's not get carried away, right? You're gonna hear a lot of things from people who go like, "Oh, this thing is a little different than I expected, and therefore cosmology is broken." And come on, man, like, haven't we heard enough of that crap over the last 2.5 years? Let's talk to you about what's real instead. So, yeah, these galaxies, they're there. We have these young galaxies, but they are not like with 100 billion stars in them. This is like less than 1% the mass of the Milky Way. These are little galaxies. Many of them are brightness enhanced because they have actively feeding supermassive black holes at the center. Many of them are brightness enhanced because star formation doesn't happen gradually. It happens in bursts. And what's going to be the brightest thing you see? The thing that's bursting right now. Another reason these things are brighter than we thought they were going to be is they made the James Webb Space Telescope better than they were told to make it. The optics are smoother, the mirror surface is smoother, it's cleaner, there's less dust and dirt on it. It's the cleanest space telescope ever built, thanks to NASA clean room technology. So yeah, it's seeing things that are like, oh, we might have to tweak what we thought a little bit. It's not like, oh, well, every galaxy is just as mature as the Milky Way, even just 200 million years after the Big Bang. No, we did find the earliest galaxy cluster, but it's a proto-cluster of only 7 galaxies. And it comes to us 600 million years after the Big Bang. The universe really does evolve and grow up. That's the big thing, though, that James Webb Space Telescope is teaching us. If Hubble was the telescope that taught us this is what the universe looks like, JWST is the telescope that's teaching humanity this is how the universe grew up. And it's because we can combine JWST data with other observatories, with the ALMA array on the Atacama Desert, with the Hubble Space Telescope in the optical and ultraviolet, with the Chandra X-ray Observatory in particular, that we were able to find the answer to a question we didn't even know that we should be asking. One thing we've asked for a long time is, hey, galaxies, big, massive galaxies that we see today, they all seem to have supermassive black holes at their centers. When we look and say, hey, if my galaxy, I know I could have big supermassive black hole, millions, even billions of times the mass of the sun. How big is the black hole compared to all the stars in the galaxy combined? And the answer is about 0.1% the mass at max. 0.1% the mass in stars of a galaxy can be the black hole. But as we look earlier and earlier to galaxies in this first billion years of the universe, that we can see them with JWST so we can measure their stars, but we can also make measurements with both the MIRI instrument on James Webb, with the ALMA array of telescopes, and with the Chandra X-ray Observatory. We can learn what's the mass of the supermassive black hole inside if it's active. And we don't see ratios like 0.1%. We see like 1%, 10%, in one case, maybe even 100%. This is profound. It's not something we expected to find. It teaches us, we've had this question of what comes first. Do stars form first and you make black holes from their aftermath, and those black holes merge and grow into the supermassive ones? Or do you have a black hole form first from things like converging streams of cold gas that makes a seed, and then do galaxies and stars form around that seed? Before James Webb Space Telescope, most people assumed it was going to be the first one. And now that we've taken this data, we know it can't be the first one. It has to be something else, probably the second one, because otherwise you cannot get supermassive black holes that are this massive from such a tiny late time seed. So we are learning incredible things about how the universe grew up thanks to the James Webb Space Telescope. But the things that it finds that surprises us, it hasn't entirely broken cosmology. It's just made us think like, okay, that wasn't what we expected. Yeah. How did the universe do this in a way that makes sense and tells a consistent story? Do we have to throw everything away, or can we explain what we know with just a few tweaks? Despite what you might have read on less reputable websites than mine, the answer seems to be the second one.
So, this is why we have you on.
To jump back for just a second, this galaxy formation is 280 million years after the cosmic background radiation being formed from the
you make neutral atoms collapse.
How far back did they overbuild JWST to go back to see wavelengths longer than further back than we conceive the universe as having existed? Like how much of an overshoot did they do?
So you're asking, what I think you're trying to ask is, what are the absolute limits that James Webb Space Telescope will ever be able to see? And does that correspond to before we expect the first stars or the earliest proto-galaxies would have formed?
Yes.
I think that's what you're trying to ask.
Yes.
So we can think about this in two ways. We can think about this in time, or we can think about this in redshift, and they're related to each other, right? The higher redshift means the farther away you're looking, which means the light is stretched more because it's traveled through the expanding universe for longer. So when we say, okay, in theory, when should the very first stars form? We're really looking at, okay, you start with this initial spectrum of fluctuations in your matter density at the Big Bang. The overdense regions are going to grow by attracting matter from their surroundings, and the less dense regions are going to shrink by giving up their matter to the denser clumps. And then it's going to get, gravitation is going to be a runaway thing, right? You start with more, you attract more, and then you're a bigger overdensity, so you're going to attract even more. How long does it take before you can form stars? The general answer for how fast you could do it seems to be when the universe is between around 50 and 100 million years old. You should start making stars. Some people say earlier. I've seen estimates that some people say maybe you can make stars just 30 million years after the Big Bang. The people who say 100 million years are very conservative. We're certain to have them by then. That corresponds to a redshift. 100 million years is about a redshift of z equals 30. 50 million years is about a redshift of z equals 50. And 30 million years, that's the earliest estimate I've seen, corresponds to a redshift of z equals 66. So if you're saying like, okay, we found these galaxies at a redshift of 14, I won't be surprised if James Webb Space Telescope sees things redshift 16, 17, 18, 20. You can probably go out there with the James Webb Space Telescope. But if you try to go farther, you run into some limits. Not a fundamental limit, but a fact that when your universe is filled with neutral atoms do this nasty thing that astronomers hate, that they block light. So if I'm only making a little bit of light, and then I've got neutral matter blocking that light, how much of that light is actually going to get through and make it to my James Webb Space Telescope? And the answer is just a little. So what I would need to do is I would need to take an image of a region of space for a really long period of time with the James Webb Space Telescope. And these impressive deep field images that you've seen, including the one behind me, Galaxy Cluster Abell 2744, which was imaged by one of these big collaborations looking for faint galaxies, they've only looked cumulatively for like, oh, we'll put like an hour on this filter and an hour on this filter. And maybe we've looked at the universe for up to like 12 hours total. If you look at the Hubble Extreme Deep Field, that was 23 dedicated days of observing time. So if you want to know, like, well, why hasn't James Webb Space Telescope broken the cosmic record by more? Well, it's only 2 years old, man. It's got like 20 more years ahead of it.
I know, and everybody has a request for what they wanted to look at.
Right,
But,
it has to share
basically, my
time.
question was:
Yeah.
is does JWST have the capability of capturing light from a 15 billion year ago universe if it's there?
Well, you'll never see
looks
that,
long
right?
enough.
Because you can only see things in terms of redshift. And if you want to see something from before 13.8 billion years, sorry, man, that was the Big Bang. 13.8 billion years corresponds to infinite redshift. You cannot go beyond infinite redshift with any instrument. So
and that's why it's like it's supposed to be opaque, and there's like the Milky Haze. We can't go past it.
Well, at some point you run into that plasma wall 380,000 years after the Big Bang, and you're just going to get like
and that's redshift 111 or somewhere all the way up there. So there's
weird stuff we could see, right? If you did see a galaxy as big and massive as the Milky Way when the universe is 50 million years old, you would be like, okay, we really got something wrong with our picture of the universe. But so far, like, we haven't seen anything that like knocked our socks off. Like those things I told you about, like Jupiter mass binary objects in the Orion Nebula and an intermediate belt around Fomalhaut and the supermassive black hole in galaxy UHZ1 that's as massive as all the stars in that galaxy combined. Those, for me, those are the biggest surprises we've gotten so far. And there are more, no doubt, to be found out there. But if you want to say, like, what are the real limits of JWST? what is the real limits of how far it could possibly realistically see a galaxy, I would be surprised if it was much greater than a redshift of 20 or much earlier than the first, 200 million, maybe 180 million years in the universe. If you want to go beyond that, I'll be honest, what I really want to get is I want to get a far infrared space telescope to go looking for this 21 centimeter line that's a signature of hydrogen spin flip. So hydrogen, right? Most common atom in the universe, one proton, one electron. When you make neutral hydrogen, which you can do in two ways, you can either say, oh, well, we had the Big Bang and then it cooled and you made neutral atoms, or you can say, oh, yeah, well, you form stars and these ultraviolet radiation from the stars, it knocks the electrons off of the hydrogen atoms, but then over time they recombine and you get electron plus proton makes hydrogen. You got a 50-50 shot when you make a neutral atom. Either your spinning electron and your spinning proton are going to form aligned with each other, or they're going to form anti-aligned with each other. 50-50 shot. If you form anti-aligned, great, you're stable, nothing's ever going to happen. But if you form aligned, there's this quantum mechanical transition that will cause the spins to flip. And when they do, they will emit a photon of very specific wavelength of 21 centimeters in wavelength. And that light gets emitted with a half-life of about 9 million years. So if you say, I'm going to do 21 centimeter mapping of the whole universe at high redshift, suddenly you're able to make a map of when did star formation happen at various times throughout the universe. Wow. So even way back in the dark ages where it says no 21 centimeter signal, no, you're going to get it, man. You're going to get a 21 centimeter signal. And the way to go see that is with an observatory that looks at even longer wavelengths than the James Webb Space Telescope is sensitive to. I want to emphasize this because a lot of people are like, are you excited about the James Webb Space Telescope? And I'm like, yes. And they're like, are you satisfied now? Did you get everything you want? And I'm like, get out of here. We have all of these different wavelength ranges that we still haven't probed with new technology in decades. Hubble is still our best optical telescope. It was launched in 1990. There's a reason why WFIRST, or the its new name is the Nancy Grace Roman Space Telescope, is going to be our next flagship mission, because it's like Hubble, but with 1,000 times the field of view. With 100 times the field of view. So it's going to be able to see so much more of what's out there. You're also going to be able to say, well, what's the next one after that? And it's called the Habitable Worlds Observatory. It's going to be as big as the James Webb Space Telescope, but useful for visible light. This should be NASA's flagship observatory in the 2030s. This should be the first telescope capable of directly imaging Earth-sized worlds at Earth-like distances from sun-like stars. If you ever wanted to take a photo, a direct image of a planet that had the potential to be like Earth, Habitable Worlds Observatory will do it. But then you say, what about these other wavelengths of light? What about the far infrared? What about the X-ray? Where's my new flagship space telescope in those wavelengths of light? And I'll just say, if we don't build it, we're leaving all this unexplored science on the table. This to me is, you don't just need one new observatory, you need a fleet of great observatories.
And it's not the kind of thing you couldn't just put in. You can't just put one instrument on one of these other observatories. Like, you'd have to have
it has to be built in a specialized fashion. If I said, James Webb Space Telescope, can I just put something on you so you can go observe X-rays? No,
I'm just imagining like all the extra things.
I need a different kind of architecture for that. I can't do it with these mirrors and these cryo optics that I've built. One X-ray photon's going to come in. I can't do anything with that. I should be building wafers with high energy resolution instead to glance the X-rays off and reflect them multiple times. I didn't build it that way. So I would say it's sort of like, you know, you don't want to do the all-in-one thing, because you know that when you
It's
buy a
never good.
product like that, you're like, oh, it does everything. Like, well, does it do anything good? And you're like, not really. It just does a bunch of
It
crap,
slices, it
right?
dices.
You want to build them optimized for what they're capable of. So you build your specialty machine for the X-ray, and you build your specialty machine for the optical, and you build it for the infrared, and you build it for the far infrared and the radio and the microwave and the gamma rays and the ultraviolet. And that's why you need a fleet. So when people talk about like, oh, fancy rocket launch, I'm so excited. I don't get excited about a rocket launch unless it's taking up something interesting to go perform something. Rocket launches for me, they're a step, right? It's like getting excited about seeing them like screwing the wheels onto the car on a conveyor belt, right? I don't want the wheels, I want the car, right? I don't want the rocket. I want the thing that the rocket's trying to launch into orbit to get up into orbit and do its thing.
So I know you have to get going really soon, and just one question that we haven't really hit on yet. You've talked a lot about what's going to be coming next with other observatories. We've talked a bit about the expanding universe. One of the things somebody in the chat earlier was curious about, like the microwave background radiation. This gets into also questions about, and you mentioned the Hubble constant and the Hubble tension. Are we seeing that? Can you just briefly explain the Hubble tension and answer whether or not you think JWST is answering that? Whether is it resolving the Hubble tension? Are we getting there?
All right, this is a big question. So let me
I
see
know
if I
it's
can unpack it
huge.
quick,
Yeah.
right? So Hubble tension really refers to, we have two different classes of methods for measuring how the universe is expanding. One class of methods is called the distance ladder method, and it basically says, okay, we see stars that are close by in our own Milky Way, and we can measure what type of star are they and how far away are they, because we can do parallax and say, okay, this is what type of star are you, and this is how far away you are. Then you can say, okay, I'm going to look for these same types of stars that I understand in other galaxies. And with telescopes like Hubble, and even better with the James Webb Space Telescope, you can measure these stars in nearby or even intermediate distance galaxies. Whereas in Hubble, a lot of these star fields in other galaxies were very crowded. JWST's resolution is so good that it can actually separate them and show you, no, these are individual stars, and we can measure them even better than we thought. So that's one way that the James Webb Space Telescope is helping with the Hubble tension. Then you say, okay, well, in these galaxies that have these stars in them, I also see some of these galaxies have like supernovae go off in them, these standard types of type 1a supernovae. So if I can build a little anchor, it's like, okay, I've got my nearby stars, and then I'm going to step out on that next rung where I've got same type of stars that I understand in a more distant galaxy. And then in those galaxies, I see these supernovae. So then I can take another step and say, oh, don't be fooled. That's core collapse supernova. I see you, Cassiopeia A. I know you. Go back to where you came from. Right? Then you see these supernovae in other distant galaxies, and you say, oh, I get it, right? Now I can measure these supernovae, and I can anchor them back here. So if you start close by, and you go farther, farther, farther away, that's one class of methods for measuring how fast is the universe expanding. And that's what gives you one value for the Hubble constant. It's about 73, 74 kilometers per second per megaparsec of distance. Megaparsec's about 3.26 million light years. Then you say, well, hang on, I got a whole other class of method. I can start at the Big Bang and say, oh, we have normal matter and radiation and dark matter, and they make these little wiggles because the matter tries to collapse and the radiation pushes it back out, but only the normal matter, because the dark matter doesn't see the radiation. So I get these little peaks and valleys. I get these wavy features. We call them baryon. Baryons are normal matter like us. Baryon acoustic oscillations. And these get imprinted into both the cosmic microwave background and the large-scale structure of the universe. So if you start back at the Big Bang and you come forward in time, oh, I'm going out of focus. Here, focus on me.
There you go.
Yeah. So either you start back early on and say, we're going to evolve this coming forward, in which case you get a value like 67 kilometers a second per megaparsec, or I'm going to start here and go out in distance, and then you get 74 kilometers per second per megaparsec. That's the Hubble tension. It depends on which class of method I use. And I saw, Justin, you had mentioned that you were really interested in the results from this DESI galaxy survey. And what DESI showed us, to me, the most interesting part of what DESI showed us is this is us looking at the large scale structure and these acoustic oscillation features that appear in galaxy clustering. If you start at the Big Bang and you say, I'm going to evolve what I know must have happened forward until I see the DESI data, you get the low value. You get the 67, I think they get like 68 point something kilometers per second per megaparsec. But if you start close by and you say, I'm going to distance ladder my way out there, you get a higher value. You get something like 73, 74. So the Hubble tension is not something that I think one observation is going to easily resolve. The Hubble tension is something where, look, we have these two distinct classes of measurement. We can either start here. It's sort of like taking your elbow and saying, I'm going to make my hand do this, and you get one set of values, or I'm going to start here and make my hand do this, and they're not compatible. They miss. They don't match up correctly. That, to me, is the core of the Hubble tension. And we wouldn't be talking about it so excitedly if we didn't have so many different independent ways of making these two classes of measurements that don't match up, and they never match up. There was a big splash made a few months ago because someone said, hey, this was the CCHP, the Carnegie Chicago Cosmology Project, probably butchered the name. That's CCCP, isn't it? That's probably something else. Those of you who are older than me will remember that very well. So, you know, there was an announcement that said, hey, we use James Webb Space Telescope to measure this new type of star in nearby galaxies, and we got a low value for the Hubble constant. It turns out that data set was very small and very biased. And if you have both of those things, if you have a small biased data set, it's notoriously going to give you any set of answers you want. The uncertainties are huge, so it doesn't tell you anything very meaningful. So if you're responsible about your uncertainties and you're saying, I'm only going to look at the lowest uncertainty values, this Hubble tension is not close to being resolved. What I will say, though, is James Webb Space Telescope offers the possibility of seeing a different type of way that could maybe say, I'm going to give you an independent method that isn't distance ladder and that isn't early relic method, because we can see you have some gravitationally lensed systems that have not just these arcs, but have multiple images of the same galaxy that are being lensed by a foreground mass. Because of gravitational time dilation, one of these properties of Einstein's general relativity, we're seeing these galaxies, the same galaxy, often weeks or months apart. So if you look at that big arc, that big pink arc in the middle of the page here, that's the same galaxy seen 3 or 4 separate times. If a supernova goes off in one of them, then you know, oh, if I see it again in Galaxy 2, and then again in Galaxy 3, and then again in Galaxy 4. This
It's the
can give you
same.
cosmic information about the universe and its expansion history and how gravity works within it. So
It's
we
like
already
using a
see.
full flash. It's like using like a flash in long exposure photography, where you get
That's
this
right. We
peak
call
of people
this
running.
phenomenon a light echo, because it
Oh
is
my gosh!
you seeing it reflect off of different images at
Yeah,
different times.
I
So this
finally put
is
it together in my head. Thank you.
bam, awesome. Science for the win. So this
Yeah.
to me is one of those huge opportunities that the James Webb Space Telescope, it can't tell you who's right and who's wrong, or why we
Yeah.
have this tension in the first place. But what it can do is it can help strengthen and corroborate one aspect of the story. It can't do anything with the early relic method, but it can do wonders for your distance ladder, and it can give you this new type of probe with a repeating supernova.
Such fascinating stuff. I have so many more questions, but we do have to let you go so you can have
Thank you for
the
having
end of
me,
your
Dr. Kiki, and also
night.
Justin.
Yes,
And
thank you for joining
all
us.
the wonderful comments those of you on YouTube have been leaving. I've been checking it out. I am breaking it down, in fact.
And you are going to be breaking it down locally here in the Portland, Oregon area. Can you tell everybody what's going on? What do you have coming up?
Hey, Portland. If you are going to be in the Portland area on November 17th, that's a Monday, check me out Monday night at OMSI, November 18th. Starting at 7 p.m., the Rose City astronomers are having their meeting, and they invited me to come give a talk, and we will have copies of Infinite Cosmos there. And I'm going to tell you everything that you'll be interested to know about the James Webb Space Telescope. I'm going to tell you how it was designed and constructed. I'm going to tell you the fascinating story of its launch and deployment, which is why this observatory that was built for a 5.5 to 10-year mission is going to give us 22 or more years of science operations. And finally, we'll explore the sights and the science and the highlights of all this has brought to us. One question I want to take from the chat. Someone was like, where's the middle of your beard, dude? I'll fess up. 2 years ago, my then boss said to me, and you, Ethan, I had a full chin curtain then. He said, and you, Ethan, you have a beard to cover your weak chin, right? And I was like, are you kidding me? This chin, I have a scar on it. It has a dimple. It's shaped like a butt. My chin has character. This is a good chin. In fact, you know what? It's been 13 years. I miss my chin. So I shaved it. Now I can see my chin and still have the facial hair. You don't like it? Get your own facial hair.
Make your own. Okay, so you're going to be in Portland, Oregon in November, but this book that we have been talking about, which is absolutely amazing. Where can people find it? The Infinite Cosmos. It is available
Infinite Cosmos,
now.
Visions from the James Webb Space Telescope. This is my first National Geographic book. Introduction by Brian Greene, words and chapters by me. I'm so proud of it. It's so beautiful. It came out wonderfully. You can get it anywhere books are sold. If you're in Portland, get it at Powell's City of Books, my favorite. If you're not in Portland, you'll have to go to the other routes. Amazon, Barnes & Noble. You can order the book direct from Disney.com because National Geographic is owned by the Disney behemoth, which you might think is a bad thing, but I got to put a Moana pun in the book. Bonus points if you can find it.
I'm going to look for that now. Oh my gosh. Someone is asking, is it only in hardcover at the moment? Is it on Kindle? Is this just,
It is hardcover in print only, but it is also available as an ebook and on Kindle.
Nice.
Fantastic. Well, thank you so much for joining us again. It's been a long time coming, and I'm so glad that we were able to make this happen. Really
Thank you so much for having me. This has been an absolute pleasure. And Justin, we even got your big Hubble tension question in.
Okay.
We got got it in there. Okay, Ethan, have a wonderful night. Is there anything, any other places you want to send people, or are you good?
Oh,
Anything else
I
before we
just want to
go?
thank everyone for the support. And if you want more of what I'm doing, you can follow me. I'm Starts with a Bang, Facebook, Twitter, Instagram, Blue Sky, Mastodon, and always check out the Starts with a Bang blog on Big Think.
And we will have links for that on twist.org. So starts with a bang. Let's finish it up with a good bang. But yeah, it's a crunch, the big crunch. Big bang, big crunch. That's where we're taking.
Big crunch is the other one.
Or the big
crunch is the other direction.
Called Starts with a Bang. I'm still not sure of how it ends. I've got some ideas.
We're still working on the end of the universe.
We're working on the end of this show here. So, Ethan, thank you so much. Have a wonderful night.
Thank you so much.
It's been just amazing. Take care. All right, Justin, do you want to talk about more science? Do we want to do that? Do you have some stories you wanted to talk about aside from? Do you have thoughts about this infinite cosmos? There's so much.
No, I'll move on to a secret tome.
This is This Week in Science, everyone.
I will move onto a secret tome that has been discovered at Al-Khazanah, also known as the Treasury building of Petra, which is one of the new 7 wonders of the world. Which I thought there were 7 wonders of the world. It turns out there were 7, and then they're like, well, there's some other kind of really wonderful stuff.
That one's not really so wonderful anymore.
They didn't take any off. They didn't delist any of the old ones.
They've talked about delisting
added
stuff.
7 more.
The new
added
wonders.
A second round of 7 wonders of the world. Petra is one of them. And Petra, if you're not totally familiar, is if you've seen the movie Indiana Jones, where was it? One of the Last Crusade or something. It's one of those. Is it the Last Crusade? I can't remember which one. It's when they're looking for the Holy Grail. They use Petra.
That was the first one, wasn't it?
Not the. Is it the? Yeah. No,
the
that
Temple
was
of Doom, wasn't it?
That was
Indiana
the
Jones
Ark.
in the Temple.
That was the Ark.
That was the Ark.
You're thinking of. This one's the cup.
Oh.
This is the cup one.
Oh yeah. Okay. Yeah.
They used anyway in the movie.
Mm-hmm.
They used Petra as the backdrop where where they were going to find the Holy Grail, or whatever it was. Anyway, I don't know my Bible history. Sorry.
All right.
This is Discovery has made an international team, including St. Andrews. Professor Richard Bates from St. Andrews School of Earth and Environmental Science led the collaboration, conducting research for the World Heritage at the World Heritage Site. This whole thing kind of came about as an accident. They were doing ground penetrating radar in the tomb because they were having some concerns about potential flood damage, and so they were checking before they did some sort of
don't put people in it if it might fall on your head.
Flood mitigation strategies.
Yeah.
And they found actually a chamber beneath the floor. So they got the permissions, and the team has now uncovered a long buried tomb containing the remains of 12 ancient skeletons. Right beneath the treasury where millions of people have been visiting every year, right below where they filmed the Indiana Jones movie. The unexpected feature is going to be in a Discovery Channel documentary, Excavation Unknown, a 2-part program airing later on this month with adventurer Josh Gates. Now, I don't know how one gets the title of adventurer. I assume
you're well funded.
I assume you get well funded, have at least spent a decent amount of time sleeping on comfortable locations, rationing provisions, having a backpack with leather straps, knowing more than 11 ways to start a fire, and being able to give a 3-hour lecture impromptu on the importance of keeping socks dry. But adventurer apparently is a thing.
I love it. A backpack with leather straps. Okay, I will put that on my list. Okay.
So the research team got permission. They did this dig. They found the underground chamber, and they began the excavation. But of course, we're going to have to wait for a TV show to really see what's going on. One of the skeletons was found holding a ceramic vessel. Initially, they say, resembling the Holy Grail from Indiana Jones, because that makes it plot twisty. But then it turned out it was just a broken pot. But it is still... But it is still very fascinating, because this is now artifacts and soil and things that can be sampled, and dating for this tomb, knowledge about the people that built it that has been, not very well forthcoming. Partly because as a site, it's been inhabited. It wasn't discovered and like unburied like we got a lot of the features that we find in Egypt were buried underneath the sand. So when we uncover them, they are how they have been for, maybe thousands of years, undisturbed.
That's undisturbed, yeah. Covered in dust.
Petra has been like a tourist attraction for almost 2,000 years. There's not a whole lot that we can discover outside of appreciating the architecture from the site itself. The finds that have been found have been pretty limited because, if there were ancient archaeologists or looters or what have you, or antiquities collectors of the past, they've probably been through the place 5, 6, 7, 8, 1,200 years ago already, to the point where. So find something untouched, buried beneath, sealed away for all this time. This is an amazing find. It's really going to, I think, give us a better picture of Petra than we've had so far.
I think that is the exciting aspect of it. It's like we've got the stuff that everybody's been looking at and walking over for a long time, but now it's extra. Yeah. It's like those extra wavelengths of light. If we had the observatories to be able to see them.
What was it? 25 millimeter radar, or 5 millimeter, whatever.
21.
We're gonna make another new satellite laboratory and put it up there.
We need to. I want it. Okay, let's do it now. This is what money should be spent on. Observatories. Let's look at things. All I want to do is look at things and then talk about it. Okay. No more Petra. Unless you want to keep talking about Petra.
No, there's nothing more on Petra. Yeah. The discovery is yet to come, but the discovery has been made, but now the data from the discovery is yet to come out. So we'll have to wait for that understanding. And then I guess I can move on to my last story of the Eve.
And from Petra and broken ceramics to broken teeth. What are they?
So this came from a series of conversations in JAMA Internal Medicine. There was an article written at the beginning of the year called "Too Much Dentistry," where there was an argument that dental diseases and procedures are being overdiagnosed, overtreated, and are costing a lot of money, and that the dental industry needs to get more scientific evidence for the rate of procedures that it's doing for people's dental health. In this article, there were some responses. Some that was like, well, hey, but a lot of the medical practices that are done in dentistry are mild. It's not all drilling and filling. There's like all sorts of other things that are going on as well. So this is maybe it's overblown that there's overdiagnosis and overtreatment. One of the things I found really fascinating on this is a retired MD also jumped into this conversation and was pointing out that X-rays for dental radiology, for imaging, Citing data, she said that in 2016, 320 million dental imaging procedures were performed in the U.S. In 2016 alone.
How many?
That accounted 320 million.
320 million. Okay.
That accounts for 40%, 46% of the national diagnostic nuclear medicine imaging in the United States. Half of our imaging technology is being used in dental. That's 320 million imaging
In 1 year. This is
in
what
1 year
this is 1 year.
for a country that had 323 million people in 2016. Like, you get an X-ray, and you get an X-ray, and you get an X-ray. And one of the things that's been pointed out.
How many people actually go to the dentist every year? I mean, this is suggesting that there's multiple X-rays for people, right?
Well, dentistry has been recommending every 6 months for a visit.
Yeah.
Dentistry has also
Yes,
been
it has.
doing X-rays for every visit, every other visit. They want to take a look, but the guidelines that are already in place now state that basically you're not supposed to be doing this imaging, this X-raying of people's mouths, until you've investigated, until you've looked in their mouth and seen something that makes you think, I need a better look at this.
No, that's not how it works.
That's not how it works.
No.
What happens is you go in and it's like, before the dentist even sees you, they're going to pour over your X-rays and then consult with you and look in your mouth, right? It's being done completely the opposite is the standard practice. Typically, those X-rays are 100% insurance billable. One of the arguments that keeps getting brought up in these conversations and the back and forth that's been going on in JAMA is that the industry is financially incentivized. That part of it is the dental decay in the United States has been on the decline for the last 50 years. It's gone down and down and down. As it's gone down, new procedures or new things or new polishings or more frequent visits have been being recommended by the dental industry. And there's very little oversight. There's nothing that has shown the safety of having children or adults get multiple mouth X-rays. There's nothing that has shown the efficacy of their
They're
treatment.
supposed to be safer now, though.
frequency.
Like they're more focused, and they don't even really put a lead blanket on you anymore. They're like, here, let's just shoot this thing in your head, and it's all like they're like modern technology. It's super safe, and they throw
Super
the
great.
X-ray thing around.
What's being pointed out is that these have not been studied.
Okay.
Uh,
All right. Great.
Like I've talked about this before. Like some of the things. Like the time I went into a dentist, and after did some swabbing and things, that like. So, we have discovered that your mouth has bacteria, and I got a very concerning look. I'm like not a surface crevice or thing on a human body in a human body where you're not going to find bacteria. But it's being told to me like I should be afraid of this because they assume. So a lot of what dentistry has done is charged people through fear. There's trust that you either have or you don't for your dentist. And it seems like it's taken advantage of. I've had multiple times when I was told I had multiple cavities or my kids were told they had multiple cavities, that a second opinion, which I recommend to everybody in the audience, if a dentist tells you the time of day, go find a second opinion. Another dentist, but still.
You should have a second opinion anytime.
I got diagnosed with 8 cavities, went to another dentist who found none. My child had 5 cavities. We went to another dentist and found none. Like the industry, like the ability to even see cavities in X-rays is a subjective thing to the point where I actually, my oldest daughter had those 5 cavities spotted in X-ray at a dentist. I wanted to see it. And so looking at me and the dentist sit side by side, staring at the X-ray, and I can see nothing. I can see that they have circled where they say they are, but I
This
can
is one
see
of the
nothing.
things. Like I look at it, I'm like, shouldn't I be able to see something? Wouldn't I? Shouldn't
And
I?
I
Like,
said
what am
this.
what am I
I said
looking for
this.
here? What are you
I said
looking
this is
for?
like,
Yeah.
I can't see anything. And like,
Yeah.
well, you're not a dentist. This doesn't come with special vision. Your degree doesn't give you different eyes. Like, I'm
No.
not seeing like, I don't know
But
what that
I will
is.
I
I'm
will
seeing nothing
right, but I will
differentiating
say there is
image-wise.
there is a gestalt that comes after looking at things in a particular way for a long enough time, which, can get looking at brain scans, very often you'll be like, "What? I'm here trying to measure the outlines of
Yeah.
a nucleus in the brain." And they are not well delineated.
Yeah.
But over time, between individuals, they're not the same either. They're kind of generally, but over time, you kind of get this idea of how they fit together. They seem to go together. And so I don't think, other people can be trained on it. That's not to say it's not possible, but there is a certain thing to seeing what you're trained to see that other people are not seeing because they're not trained yet. So I'm not saying that your eyes can't see it or wouldn't see it, but maybe if we all got a little bit of training on looking for cavities in
Yeah.
X-rays, I
But
don't know.
when we went to the
Yeah.
second dentist, the second dentist also couldn't see them. So I feel a little
Okay,
justified
fair enough. There you go. Okay,
that
fair
there
enough.
was nothing there.
Yeah.
So one of the things these papers are bringing out is there's no justification in any kind of scientific literature for seeing a dentist every 6 months. There's nothing there. When you hear dentists
But what
recommend,
about prevention? If you go every 6 months, then maybe because you're there, they're better at it's just better,
there is
right?
no scientific evidence that a 6-month interval helps in prevention.
Okay. Nobody's looked at
It's
that specifically, or it hasn't
no,
just
and
coming
it's
up in
more
the evidence.
likely
Yeah.
a year to 2 years is more than sufficient. There's not great scientific evidence, no scientific evidence really, backing up a lot of the claims made in dentistry. What typically dentists are recommending are things that are covered by insurance.
Yeah.
We're not talking now, like I split a tooth once, and to this day now, I cannot tell you which tooth it was that got replaced. Dentistry is amazing. And it may be that for dentistry to be that amazing, that I can't tell which was the real tooth and which is like the fake one, where it is. Maybe it's amazing because they are having to scam people and insurance companies for multiple polishes and x-rays and all these things to keep their practices afloat, to become proficient at what they're doing. Maybe that needs to be part of it, right?
And to catch the things so that they can help. Like maybe there is a part of it where it's like if you keep the thing going, then the insurance is paying for it. And when the big thing happens, the insurance will pay for it. Like maybe there's something to that. Also keeping the practice, like you said, keeping the practice afloat.
Yeah.
I don't know. Yeah, I've had those experiences where the dentist is like, "There's a crack in your tooth," and I'm like, "I don't think there's a crack in my." What do you mean? "Oh, no. We need to fix this." And then suddenly there's drilling involved, and I'm like, "Why are you drilling a crack?" "No, we have to drill so that we can then put a filling in to fix." Meanwhile, or go ahead like 2 weeks, I'm still in pain because the filling was done wrong and I can't chew right and it's hitting something and it's painful. My husband stuck a freaking UV flashlight to cure the resin for the filling. My husband sanded and cured the resin himself at home because the
Oh
dentist did
gosh,
such a terrible job. Now the dentist is
home
like, "Oh,
dentist.
well, your insurance isn't gonna pay us enough, so we're not gonna have you as a patient anymore." And I'm like, "That's okay.
Yeah.
I would like to find another dentist."
Well, and it's
I
too
would
late.
like
So
to
I
go
won't say it. I won't say it. But if you had gone to a different dentist for a second opinion, they might not have drilled.
Mhm.
There's not an oversight or a consistency with the practices. There is no oversight. There's nowhere else. This is also pointed out in the conversations that
I just want a
have been
good
taking
dentist
place in
who's
JAMA.
nice.
There's no other medical field profession scenario where the person that you come in and does an initial investigation is also the person who operates the diagnostic equipment, interprets the diagnostic equipment, and then performs the procedure based on their own determination of what needs
Yeah.
to be done. It's the only medical area of profession in healthcare where all of that is done in-house and doesn't go to multiple outside people to then relate back.
Interesting.
We're going to wait to get your results from the blood folks. We're going to wait till the x-rays come back from we're going to send you down to somebody else to do some imaging, and then they're going to interpret that data and send that a report back to me. We're going to send your swab. I'm going to send it to the lab, and they're going to send me back a result from that telling me what it is. No, at the dentist is like, I've looked at everything. I did the diagnostics. I've decided what this problem is and what the solution is. And turns out it's billable by insurance companies, so it's only going to be one afternoon in the chair. There's a problem with zero oversight. And if anybody has had experiences like that, which I have had I've had like a dozen of these types of encounters where I know I'm being lied to. Right? Or I know that like when there's bacteria in your mouth. I know that person is trying to leverage a word that can be scary to the public in an attempt to manipulate. I've seen this. So I know like this industry has been riding with a lot of on the confidence of the general public.
There needs to be more oversight, and I think that is that what these researchers or these dentists who are having the conversation eventually came to? Like, is this conversation done that's happening in the medical journal, or is this?
Well, it's still ongoing. I think it might still keep going. But one of the things that all of the parties who are sort of agreeing on, who have weighed in on this, is that there needs to be rigorous scientific studies conducted on practices in dentistry to see if there's efficacy, to understand if they're even necessary, to test the safety of the frequent X-rays, and to see if they're even the current guidelines that are there are asking the industry to reduce the amount of exposure they're putting the public to for X-ray technology, and not to even do it until after they've analyzed it, looked in the mouth, and found if there's a reason for doing it. So basically, it's asking for an oversight of this industry. Somebody's saying, wasn't I talking about flossing being a scam? I think flossing is a scam.
No.
Take care of your teeth. But like the whole point of this too is like
your teeth. It's good.
Awareness of dental health has gone up so much since the 70s that cavities or white spots or things like that have massively declined over the years. General dental health in the United States is better than it's ever been. Because of that, though, was one of the arguments in this. In the initial story, it seems as though dentistry has pushed for more and more frequent visits than used to be asked, and is trying to treat things like white spots, which aren't actually cavities. It is creating new treatments to stay financially viable because of how much better brushing teeth and flossing teeth and this sort of thing has affected their business.
It's the vibrating toothbrushes, everyone.
That's what's taking them down.
It's taking them down. I mean, it's great that helps so much, and that we have these technologies that we can use in our own homes to manage our own dental health. But this is, like you mentioned, an issue because the science needs to be solid behind dentistry and the way that it's applied. Similarly to medicine, like this is something that affects health. We know now bacteria in the mouth and with infections, especially gum infections, can lead to heart problems. So the dentist is very often on the first lines of seeing potential problems that can end up becoming bigger medical problems.
Mhm.
And then there are the problems that happen, like you said, the broken tooth, the need for a root canal, like these things that happen that ugh, you have to go to a dentist to get them taken care of. And how do we make sure that there are enough dentists down the line? How do we make sure that our teeth are healthy? We want preventative care, but we
Yeah.
also do need crisis care and ongoing care like that. So how do we make it work?
Yeah, so my point is that it's a
Dentists,
scam,
police
and it's not a scam at the same time because it's so we need both.
It's the
At this
basic
point, this is how
duality
the
of
system. This is just
humanity.
how the system is operating. But if it's you, go get a second opinion every time. Never take the first word of because there is no oversight, and 5 different dentists never agree. 5 out of 5 dentists never agree. Might get 4 out of 5, but never 5.
Yeah, we know that for sure. I've seen it in advertisements.
All the time.
All right. All the time. Okay. Moving on from Petra and dentists, let's talk about the Force.
Which one?
How could you use the Force if you were a rodent? Well, it wouldn't be the Force. It would be a force. And it's kind of a fascinating study. Researchers have been curious for a really long time. Blair's talked about like the pitched ultrasonic vocalizations that rats and mice make. Lots of rodents make them. They discovered these sounds back in the 1950s. And they think there's been consensus about, okay, this is social communication. There's thoughts of that this is, love songs, that they're like birds, that these high-pitched things that we can't hear, but that they've been able to detect might be, these really special conversations between lover mice or lover rats. Anyway, so a new study has just come out. Researchers at University at Buffalo have just published in Neuroscience and Behavioral Reviews that, oh no, these aren't love songs, but the ultrasonic vocalizations are used to enact a force on the air to vibrate air particles and waft them into their noses in a way that is better for their olfaction so that they can detect food, danger, the olfaction is incredibly important for rodents. And that it's this force, the ultrasonic vocalizations, quote unquote, says Eduardo Mercado III at the UB College of Arts and Sciences, they're creating new pathways of information by manipulating their environment and controlling the molecular interactions of particles around them. It's not love. It's not social communication, although it might play a role in that as well. We don't know. But he says, it's so far off the scale of what we know. It's like we're observing Jedi rats. And I think that's really funny. I like the idea that these rats are Jedis. Vibroacoustics is a field of work. This is artificially producing ultrasonic vibrations, making airborne particles cluster, and that this researcher suggests that that's what rodents are doing, making it easier to detect and identify various scents. So now the next step is to move forward into actually studying this and determining exactly if this is the reason that it works this way, that's why they're making these ultrasonic vocalizations, or is it that they're communicating and happening to do this at this? Does it have multiple functions? We don't know that for sure. Right? Yeah. It gives you a different idea of, we think of vocalizations as, of course, it's communication. Of course, it's something like, but maybe that's not what it's all about at all. A boom. I'm making the dust vibrate in my room. Achoo. kidding. Moving on with my sense of things. Have you heard? I think we've talked about it on the show, but have you heard of the man-eaters of Savo, Justin?
I do not know what that is.
Okay. There's a famous story, or well-known story about what are called the man-eaters of Savo. These are two large, maneless male lions, wild lions, Panthera leo, who in 1898 and around that time were terrorizing railroad construction workers in Kenya and Uganda in the
So
Tsavo
I think,
Valley.
I think there was, I think I saw a movie about this a very long time ago. My goodness, like a very, very long time ago must have been. But yeah, like these lions were like hunting people. Like they were like
Hunting people.
doing people murder.
And that's the story. The story is, oh my gosh, two lions were killing people, but there's no evidence of it whatsoever. It's like they're like,
I saw a movie that it happened in, so it
but
must have been.
did it really happen, or is it just a story?
It might just be Hollywood.
And anyway, so the lions ended up on display in Chicago's Field Museum, and there's been lots of hairs extracted from the teeth because they didn't floss. And so the researchers back in the early 2000s, when the lions were on display.
Wait, so they taxidermied these lions, but never but the teeth somehow still had victim in it?
Yes,
That
yes.
makes so little sense.
Yeah, the victims were collected, but the methods were not available. And, just like there's a lot of stuff to do. It's like, whatever, field specimens, blah, blah, we'll collect some samples, blah, blah, and they get put in a drawer, right?
Okay,
Or
the drawer specimens, they're not like, okay. I was picturing like taxidermy display, but that would be a whole different process.
the
Okay,
teeth,
so
the hairs taken out of the teeth were taken out of the teeth a long time ago, but yeah, they extracted a bunch of hairs, thousands of hairs from a cavity in one of the teeth. These lions did not have good dentists. And
The
anyway,
Ghost in the Darkness, 1996. Thank you so much. Yes, that was the movie. Thank you, Chad.
The researchers did not have the ability decades ago, to genetically figure out what the hairs belong to, what's going on there. But ta-da, fast forward to the future. We've got all sorts of great technologies to be able to determine what's going on. And so the researchers for this particular study that was published in Current Biology finally got around to looking at what was in the hairs of the teeth. And yes, there were lots of prey species. They saw hairs of yummy things that lions are known to want to eat, and humans. So yes.
Dun, dun, dun.
Yes, indeed. Human DNA was found in the combination of genetic information, the mixture that identified giraffe, human, oryx, waterbuck, wildebeest, and zebra as prey. The interesting thing, so we have the stories about the terrorizing of the people. We look at the area around 1898 and it's like, oh, hey, all these animals hang out in this Savo region, except for the wildebeests. And so the researchers are like, what is going on? Wildebeests are like 100 kilometers away usually. And so the question, and they thought at the time that the wildebeests weren't there either. So now the question is, why were the lions eating the wildebeests? Was it because the wildebeests were roaming into the Savo region at that time and they were like, lions, and they left? Or were the lions hunting in a much bigger range than would normally be expected? And they don't know the answer to that question. But what's really wonderful here is that years ago, 100 years ago, over 100 years ago, when the lions were shot. Nobody knew that this kind of information would come out of it. So it's really wonderful to be able to have this historical perspective on a story
Yeah, I
that
guess,
became a movie that is,
well,
that
I
is
guess it does some
culturally relevant.
I guess it does lend then corroborating evidence to the murder lion story.
The murder lions. Yes. The man-eating lions of Savo.
Because really that movie is like, well, let's remake Jaws, only this time instead of a shark, it's gonna be a lion, and then they're like, oh, lions, I don't know if they can swim. No, it's not gonna be in the
Doesn't
ocean.
matter.
Oh, then what would be the point of having the boats? No, we're all, look.
No, we got trains.
Never
We got
mind.
people,
Forget that I
we've
said
got people
Jaws.
building a rail. It's great.
We're gonna make a lion movie. Oh, okay, that makes sense.
And instead of the dun dun music, then it's like
we're gonna play the circle of life. Humans getting devoured.
No.
that music playing, arcing up as humans are like, ah.
Oh,
no.
that's hilarious. All right, moving on from man-eating lions of Savo. My final story for the for the night. This is all because Blair's not here, really. Has to do with there's a few wrinkles to this story, actually. Has to do with the wrinkles in elephants' trunks.
We still got the.
Oh, I
lion
know. Okay,
tail
I didn't
data
take it
pic.
down. All right, but the wrinkles
Just
in
making sure.
Thank you. The wrinkles in elephants' trunks. Have you ever looked at a elephant's nose and said, "Gee, elephant, why is your nose so wrinkly?"
No. I figure, though, it makes sense. It's got like a segmented looking kind of thing, a little bit to it there. It's a bendy thing, you got little muscle attachments going along there.
Yeah,
Figure it kind of makes sense.
but not every elephant has the same wrinkles. They're different. So researchers,
like a fingerprint.
Yeah,
or an earlobe.
Ta-da!
All right.
And here you go. Yes, researchers at Humboldt University were looking at the brains of African savanna elephants and Asian elephants. And then we're like, oh, your brainstem is really interesting. What's going on with your brainstem? And they found that this little area of the brainstem, they say it looks kind of like it's about the size of a fava bean. I like fava beans, the good class of Chianti. Anyway, fava bean brain area had a bunch of stripes in it. And as they were looking at the development of elephant embryos, they were like, oh my goodness, these stripes match the wrinkles in the elephant trunk. You can see the wrinkle in the nose or the trunk in the brainstem. They look the same. And so they kept looking and looking and looking. And for this study, they find that during development, the number of wrinkles doubles every 20 days. At very early in development, there are only about 4 wrinkles in the trunk and also in the brainstem. And as the elephant grows, you have this doubling. It grows and grows and grows. African savanna elephants don't have very many wrinkles added as adults, but the Asian elephants actually add lots of wrinkles as they grow older while they're adults. So their whole life, the Asian elephants are adding wrinkles to their nose. So does this mean that they have greater dexterity? Do they have different use? If you think of the wrinkles also being added in the brainstem, like there's some learning going on there. There's a lot of change happening because the brainstem is also plastic as the elephant is getting older and growing as the elephant is using the trunk for grasping. So the African savanna elephants are more likely to use the tip of their trunks for pinching objects. Both of them use it for grasping large things. But really, the Asian elephant is more likely to wrap their trunk around an object than to grab it or pinch it daintily with the end. Additionally, there are left-trunked and right-trunked elephants, and that affects the wrinkles as well, and can be determined in utero before the the baby elephants are born. Yeah. Anyway, the elephant trunk, it's wrinkly for a reason. It changes as development occurs. It's changing the brain of the elephant as an individual gets older, and it's pretty interesting. Right-sided, left-sided elephant grasping is determined. Symmetrical goes to asymmetrical. Pinching, grasping, it's species different. They need to look at some more species. They need to look more specifically at the brainstem. But really, it's so wonderful. It's kind of like the barrel cortex of rodents, where you can see where the whiskers are in the brain for the tactile aspects of touch. This is going to give a very specific area of the brain to be able to correlate with behavioral movements and use of the elephant trunk. And so now, when somebody says, "How did the elephant get its wrinkly trunk?"
Now you know.
Now you know. Now you can answer that question.
Very cool.
Yeah. Some of them are born with it, but some of them, they grew with it.
This, while you were telling that story, I had to go and look something up.
What's that?
There was a 12-year-old lion named Cecil
Oh, more
who
lions.
was living on a refuge. They got lured off the refuge and was killed by an American trophy hunter from the United States, Mr. Walter Palmer. Mr. Walter Palmer's profession? Dentist.
Oh my gosh, this comes back to the teeth so much. Teeth and lions. Who knew? Maybe they'll have to get the hairs of the victims out of the elephant trunks? I don't know. That's not the same. It's not going to work.
$50,000 to have somebody lure the lion off of the refuge where he shot the old lion. So proud of you, Mr. Dentist.
Good job, Mr. Dentist. That's just rude. That's like, I don't even know how to do this job, so I'm going to cheat. People, jeez. How do they determine trunkedness? Researchers look at how the elephants grasp objects, whether they grasp from one side to the other, and whether they have a predilection for grasping one way or another. Now we have to find out whether or not the elephant teachers are like forcing the elephants to be like right trunkers as opposed to left trunkers. And how does that affect their later life and their learning ability?
Yeah, I know. It's a big concern. My youngest is he might be one of those freaks that
no.
can never use a normal pair of scissors.
Good for him.
Like, other than that, I don't know how many other things that affects.
Really.
But the one big one that's always stood out is like you hand somebody who's left-handed a pair of scissors, and they're just like, "I'm sorry, I can't. I can't operate scissors. Just don't work." And it doesn't make any sense. But if you've ever tried to use a pair of left-handed scissors or operate scissors with your left hand, I guess, I don't know.
You say, "I can't. It's not working right. Why don't these work correctly? What's happening?" And I used to be ambidextrous. Not so much anymore. I can bring it back. I'm still young. I can learn new tricks. You know what my new trick is? No, I don't have a new trick. Are we done with our stories? Have we done it?
Yeah, I think that was it.
Okay. Same old trick. Thank you for joining us for this episode of TWIS, everyone. We hope that you have enjoyed this show. I got to give shout outs to everybody who's listening, watching right now, especially people in the chat rooms who are here with us live. Oh my goodness. YouTube, Twitch, Facebook. Thank you for joining us, for commenting, for being a part of the conversation. It's been so much fun tonight. Such great conversations. But Discorders, I see you. Thank you so much for chatting and being there. Thank you to Fada for helping with show notes and social media. Thank you to Identity4 for recording the show. Thank you to Rachel for editing the show. Thank you to Gordon, Arnlore, and others who really help keep those chat rooms nice, happy places. And hey, Discorders, this is you, because the Discord people are Patreon sponsors. That's what happens. You got to sponsor, got to support us on Patreon, and you get to join the Discord. So thank you to our Patreon sponsors, because no show would be complete without this moment of thanks. Thank you to Eden Mundell, Alan Viola, Aaron Anathema, Arthur Kepler, Craig Potts, Mary Gertz, Teresa Smith, Richard Badge, Bob Coles, Kenton Northcote, George, Goris Beer, Vela Zarb, John Ratnaswamy, Chris Wozniak, Vegard Chefstad, Donathan Styles, aka Don Stylo, Ali Coffin, Reagan Shubru, Sarah Forfar, Don Mundus, PIG, Stephen Albaran, Daryl Myshak, Andrew Swanson, Fredus 104, Sky Luke, Paul Ronovich, Kevin Reardon Noodles, Jack, Brian Carrington, David E. Lingblad, Sean Clarence Lamb, John McKee, Greg Riley, Mark Hessenflow, Steve Lee, Sminik, Zima, Ken Hayes, Howard Tan, Christopher Rappin, Richard, Brendan Middish, Johnny Gray, Remy Day, T. Burton, Lattimore, Flying Out, Christopher Dreyer, RDM, Greg Briggs, John Atwood, Rudy Garcia, Dave Wilkinson, Rodney Lewis, Paul, Philip Shane, Kurt Larson, Greg Landon, Sue Doster, Jason Olds, Dave Neighbor, Eric Knapp, Lon Makes, E.O., Adam Mishkan, Kevin Parachian, Aaron Luthen, Bob Calder, Marjorie, Paul D. Disney, David Simmerly, Patrick Pecoraro, and Tony Steele. Thank you. Thank you for supporting us on Patreon. And if any of you would like to support us on Patreon, please head to twis.org and click on that Patreon link. On next week's show, we're going to be talking with somebody else, Dr. Stephen Rouse, about drinking recycled water. Special recycled water.
Nice. And we'll have a Blair. We'll have Blair back.
We'll have a Blair. That's right.
We will have her back on Wednesday, 8 p.m. Pacific time, or 5 a.m. Thursday, Central European time, depending on your choice of shows. Broadcasting live from our Twitch, YouTube, and Facebook channels.
And if you want to listen to us as a podcast, just search for This Week in Science wherever podcasts are found. And if you enjoyed the show, get your friends to subscribe too, please. Yes.
Yes. Borrow their phone. Subscribe them. When they're not okay, it's fine. For more information on anything you've heard here today, show notes and links to stories will be available on our website, www.twis.org. And you can also sign up for a newsletter.
And we love your feedback. So if there's any topic that you want us to cover or address, I know there's a couple emails out there that I have to dig into and make happen, or a suggestion for an interview, please let us know on one of our social media accounts. Yeah, we've been using those a little bit more, especially Blue Sky. I like it over there. Or send us an email. I don't know. Just put TWIS in the subject line of those emails. Emails are best. We like the emails. Just do that. Yeah. If you don't want your email to get spam filtered into wherever it is that H21 hydrogen, neutral hydrogen spin flip signature is, because we're not looking at that. We are not looking at it at all. And so if you don't want it to be spam filtered along with that, make sure you put TWIS in the subject line.
We look forward to discussing the science with you again next week. And if you learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This week in science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth, and I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 I've got one disclaimer, and it shouldn't be news, that what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may...
You just may understand. If you listen to the science, you just may. We are in the after show, but I don't know how long it'll go because it's late at night and I haven't had my dinner tonight and I don't know what Justin's up to. It's probably like 7:30 a.m. there now finally. But he's probably got a family and a lot of stuff going on. Probably got a lady friend who's got to go to work and a baby he's got to take care of. Whew. That was a good show full of lots of science, wasn't it? That was a lot. Yeah, Kyle. I know. The science makes me sleepy too. Got me. I was very excited by all that. Tonight, I am science excited. I am. Noodles. Yes. Is it calendar time? Got to talk to Blair and see what we're doing. How many people got last year's calendar? That's my question. I need to figure out how to actually print a calendar. Last year was a whole thing. Nobody wants to make a calendar the way that we want to make a calendar. So it makes it very difficult. You have to have the money to be able to do all the things that you want to do in the way that you want to do them to make the money. It's a very interesting conundrum wrapped in an enigma. You got one. Thanks, Paul. Disco Science. Yeah, I was singing a whole song there. I don't think it was a good song at all. It was terrible. Chock full of science. Oh my gosh, I love it. We should trademark that. Thank you. It's ours now, everyone. We're saying it here, so now you know. You can't have it. We're chock full of science. Oh, yay, Noodles, you have last year's calendar. Good job. Thank you. I'm so glad. I like the calendars. I want more physical calendars. I like them. I like hanging them up, and I like giving them to people, and I like all the things. Yeah, so we have a show next week. If you have more black hole questions or JWST questions or any of those things, make sure that you reach out to Ethan Siegel, our guest tonight, over It Starts With a Bang. Enigma Variations. Robert Varner. Wow. Yours is up in your home office. Oh, thank you, Eric. That's great. I love it. We all need more calendars. How many years has Blair done the calendar? Maybe we need a calendar of calendars. I don't know. Oh my God, I saw Justin's head. No, I just want to say goodnight. How hard it is. Fantastic. Own the domain. That's it. That's right. Hi. Got your earphones back.
Hello again.
Hey.
Yeah.
I'm having fun.
Did we finish the show?
Uh-huh. Yeah, we did the whole thing.
Oh my goodness.
Uh,
What was it? Val Kilmer and who?
I love
I think for some reason I saw that movie in a theater.
that movie.
The lion preying on people. The ghost.
I never
The
saw
Ghost in
that.
the Darkness. I don't know why I saw that movie though. It doesn't seem like a thing that maybe it was a thing I wanted.
I just remember Life of Pi, reading the book, and then I don't think I ever saw the movie because there was no way I wanted to see that movie. But I loved the tiger that wanted to eat him, but then he like basically lived on the raft with the tiger, and it was fine.
I don't know.
Eric Knapp knows. Michael Douglas, 2017.
Okay.
Oh, people have calendars from this last year. What are we gonna do next year? We need to talk with Blair. Don't know.
Oh, I don't think Blair's on it this year. Maybe she'll surprise us. We'll find out next week.
Yeah.
Blair's back. Blair's
For a
back.
week. Only for 1 week. 1 week only. Tonight has been the night of like the sales pitches. The slices and dices. Available for 1 week only. Yeah. Blair will be back next week. That's good. Do you have a hard out next week?
Nope, I'm good.
Okay, you're good. Great. So we'll have fun. I can't wait. Did you have fun tonight?
Yeah, I didn't get to get into any of the. I wanted to ask a bunch of questions that we didn't get to, but I think I
tried.
I realized. Well, yeah, but I think it also is we're gonna need a Sean Carroll.
Yeah.
We're gonna need somebody who can entertain those ideas, whose career has already. You will get drummed out of physics, academics, and maybe deals with National Geographic if you're even engaging in conversations about space-time contraction, redshift, tired light theories. So
I'm a redshift tired light. I mean, I'm like rubbing my eyes. I'm like, I have so much sleep in my eyes all of a sudden.
I think I got one of the questions I answered though. I think I have to go back and rewatch the show to see how it was answered, because what I wanted to know was if JWST had the capabilities, and I think it does, of seeing those really long wavelengths that would push back beyond what we have benchmarked currently as the age of the universe.
Yeah,
because it's a super cluster of galaxies back there that we keep finding older and older and older. Like, we kind of glossed through it, but the prediction for most of cosmology after the Big Bang Theory was that there wouldn't be galactic formation in the first billion years. This was
a long time ago.
Of course, but it's been augmented by evidence, right?
Yeah.
Yeah. It's one thing to have made the predictions based on the models, which most of which came from Einstein. He didn't like have the Big Bang Theory. He didn't have an expanding universe. His equations actually showed
right
that the universe that he had modeled would either be expanding or contracting. But he didn't like it. It was unconventional, too unconventional even for Einstein. So he created something called the cosmological constant,
right?
Which is an equation he basically put in to balance things so that we would have a finite space-time that was neither contracting or expanding. He had to fix his model. And then Hubble, not the telescope, but the man, observed the redshift, which implied that the universe was expanding. And then Einstein was like, oh, that's my biggest blunder. I shouldn't have put that constant in there. My model showed that it was going to, but he didn't want to flip the coin with the universe.
Mm-hmm.
So he placed that in there.
I think if we were to have had more time, or because he is very interested in the theoretical aspects of the Big Bang, and I've had some really interesting conversations with him about how, like, we think of the Big Bang as like this, that's the beginning of everything, but actually there was this whole like Big Bang, there was this like inflationary period before the Big Bang, and then the thing that, and then there's like all these different parts. It's like, oh wait, there's like time before the Big Bang, and this is the thing. It's kind of crazy, but
And,
I
and,
think
and
like
then time is a
what
whole
Pamela
kooky
is
thing
saying,
before
but
Big
what
Bang.
Pamela I think is saying in the chat is, if the universe is older than that 13.8 billion years,
Yeah.
how would that change the light? How would be, can we see, if the way we're measuring it is telling us it's 13.8 billion years, but what if it's older and we're wrong? And yeah, I don't know. Should we be
And
measuring
it doesn't
different
mean
light?
that it doesn't mean you have to transform all cosmology, right?
No.
Like the cosmic background radiation to 290 million years is not a lot of time for everything. That is because the CMB is supposed to be from the completely condensed spacetime. The reason that it's homogeneous is because everything was in one place, and then it expands, and then 290 million years later, we're finding these galaxy formations, not
But because
star
it
formations,
condensed and it started
not star
mushing and
formation,
pushing,
galaxy
it got
formation.
heterogeneous. And what I'm interested in is that difference in the time. And is it always the same everywhere? Because is time or the expansion different at different times and different places in the universe?
Right, and it's
Right?
and so
That's the other
what
question.
part of what getting into the Hubble tension was about is not only the Hubble tension is why we think not only are things expanding, but this rate at which it's expanding is speeding up.
Mm-hmm.
And I think DESI, which has still got data drops coming, kind of actually narrowed that down so that it looks a lot less like there is an acceleration to the expansion. Meaning, if part of what those different looks, where he was talking about the ladders versus the deep redshift of the cosmic microwave background radiation, a lot of that data is old. That gives us this Hubble tension. So DESI is the newest version of being able to look at this, and it's saying, maybe that tension is a lot less severe, which would mean more of a constant expansion. The thing with a constant expansion is,
wasn't it JWST and Hubble though? They just looked at like, instead of like the 50 stars, it's like they looked, or supernovas, they looked at like 1,000 or 1,500 or something, and it confirmed basically.
DESI has, I think, millions of galaxies in its data source.
Right. But that's just a different measurement yardstick.
It's grabbing redshift and some. But one of the things though that's been argued against things like tired light, meaning like maybe light doesn't lose energy, but just transfers energy into redshifting and spreads out, because it's not actually losing energy. It's just changing its conformation and maintaining the same energy when things redshift. One of the things that knocked down the idea that this redshift is that we're seeing isn't necessarily from an expansion, but from a change in just the light itself and how it's redshifting. One of the arguments against that was that acceleration. You could fit a tired light theory into a constant expansion. It would fit with there. But if there's an acceleration to that expansion at all, if it changed or was dynamic and changed over time, that would tired light type theories. And there's like 30 of those. So you have to be very specific and just say all that you're referring to is that light can redshift over time. Not that it's losing energy or because of any other making up physics, but you just say that light over long periods of time and traveling through space can redshift. The accelerating expansion rules that out entirely. because then it's at one point
Yeah.
it's changing like this, and then it's shifting differently later, and then you're having to invent an entire universe of physics fixes to make it work. But if the Hubble tension gets knocked down, meaning there's a consistent expansion throughout all of time that is uniform, then something like an affect of normal redshifting happening to light as it travels long distances fits. So that's where I was going to go with that. But we might need
maybe we'll have to find somebody like, I mean, Ethan was great, and maybe we can get him back on to have like a
Ethan's great, and actually his some of his explanations of the JWST are things that I had not heard from other places or other sources.
Exactly.
He's absolutely, it was absolutely fascinating interview.
But the problem is that
I didn't even know about the hydrogen spin situation. Like,
I know, I'm like,
now I want a whole
okay,
new observatory just for this. That's
oh yeah,
amazing.
he got us voting.
I didn't know that
I'm
was
like,
a
yes,
thing.
let's do it.
Yeah,
I want that one. But yeah, I mean, the thing is, he had wonderful things to say, but we didn't have like 3 days with him. So, but yeah, so, maybe we can get Sean Carroll on, maybe we can get, there's all sorts of people, but to have some deeper conversations about the Hubble tension and the
I need
different
three things
evidence.
explained to me. I need to explain. I need somebody to explain to me how that redshift is not the only metric by which we're determining distance and of the ancient. I need somebody to explain to me that expanding space-time is stretching light, because
that's what he was talking about.
Doesn't make any sense to me. And I think I just need another couple of conversations for somebody to explain to me, because that is almost the description of gravitational redshift. Gravitational redshift is happening when space is stretched out again near matter, gravitation, like mass, like a massive objects are when you leave the gravity well, there's redshifting, right? Because the space is actually stretched out there. There's no contention that anybody's making that space itself has this massive gravity to it that would create a gravitational redshift. That's considered a separate thing, but it's the expansion of the universe itself, of space-time, which means a finite space-time that is stretching without interacting with mass. It just doesn't make that, based on the rules of how these things were constructed. It just doesn't make sense to me. So.
If you want to, Ethan has an answer. Ask Ethan, number 39. Why does light stretch as the universe expands? So,
what's the answer?
It's probably longer than I don't know. It's not easy. Let's see. General relativity is involved. He goes back to the beginning. He's going back to first principles. Okay, hold on. I can't answer this question. Here's the link. I'm going to put it in the chat for everybody. Here's the link. And then a lot of people have talked about it kind of like like leavening dough, where the dough rises if you've got raisins in it. The raisins are closer together, and then as the dough rises, the raisins get further apart. And because time and space are intricately connected, because the space expands, so does the time.
So the problem with that model and the balloon model, where they have the dots on the outside of the balloon, they can give you the concept of how a thing 2 dots over seems to be moving faster away from you.
Right.
Right. However,
Because you're
matter
moving
is
away
not,
from it at the same velocity-ish as it's moving away from you, right? Isn't that
however,
why
this actually, that model is terrible because it's not what's going on. And it's predisposing because no matter is fixed to points in space-time. That's not how it works. And so when you're talking about space-time expanding and distances become greater because space-time is stretched out, it almost is a picture of a absolute space with things, matter being pinned to points in that space and carried along in space-time and carried along with it, which doesn't seem to be like based on anything.
So we have the stuff, dark matter, and gravity that kind of keeps stuff locally connected to stuff locally, right? And then you're still connected by the connective tissue of the universe to
gravitationally bound systems.
Yeah.
Yes.
So he says here, since the energy of light is defined by its wavelength, as the universe expands or contracts, the wavelength gets stretched along with it or compressed if there's contraction. And so when that happens, because the wavelength is expanding, stretching, it's going to get red shifted or blue shifted because it's changing the wavelength itself.
Yeah.
But you know this. So
yeah, and this is the part that I'm like,
this is I don't this is
the amount that space is actually expanding compared to the speed of light. Like, it's sort of like the graviton problem. The graviton problem would be that the graviton has to be communicating with every piece of mass everywhere in the universe, back and forth at the speed of light constantly. It requires an immense network of energy communicating that we don't see any evidence of. The same sort of thing seems to apply to me for this stretching out of wavelengths due to an expanding universe. The rate of expansion is actually very, very small. Like, as a fraction of the speed of light is almost insignificant. It's just that the universe is very old, so that it can become visible to us. That's why we don't really see it in our local regions. There's not enough time to cause redshifting in between us and our nearby galaxies. But that also means that the light has to be ever stretching by quantized space-time, stretching it out as it's passing through this geometry.
Now you're like getting at like what is space time,
and if there isn't a definition, which, by the way, actually, depending on who you're talking to, there isn't. The only quantized version of it is loop quantum gravity, and that's a rabbit hole that's produced nothing. The quantum field theories have quantized versions of gravitational fields, but not of space-time itself. Einstein's own view is much closer to ether theory, and he actually gave a speech in 1920 where he can't imagine relativity operating without an ether medium for energy to be passing through. But it wasn't the classic luminiferous or the previous ether, but it was built by all the people. The mathematics and the tensors behind the geometry that Einstein worked with was all ether theory.
Yeah.
So the big question I want to pose at some point is, what would a contracting universe actually look like? A contracting space-time? Because that same picture that was up there of the balloon, right, with the dots on the outside, is the balloon.
Right. What if it were going the other direction?
If instead you took those dots and suspended them in fixed points within the balloon, right? And now we're compressing the balloon. You get a report back from one of your inhabitants in one of the solar systems in one of those galaxies that are floating in the balloon. And they go, hey, what's going on out there? Our entire universe has just expanded. Everything got further away. That doesn't make sense because we're condensing the balloon with the little pieces in it. We're actually shrinking. Well, what we've done is we've created a higher density, a pressure density of all of the molecules of oxygen, if it was a balloon or whatever, of air. And it turns out the phone call we're getting from that planet in the solar system in that galaxy has been determining the distance between it and other galaxies by the number of air molecules that are between it and the other. And as now we've created density, things now will seem further apart. So I don't know. If you were actually telling me that the expansion of the universe was an illusion of greater distance being created between places, that would make sense. But instead, they're saying they're almost saying there's no greater distance. It's space itself stretched, which caused the wavelength change. Not that a distance increase has caused the wavelength change. So this is and then what is the space time that is stretched? Oh, we have no definition of this.
No clue.
We have no explanation for that. we this is how it's been decided.
Yeah,
Decided that it is, and so there it is.
What was there? Was another one. Yeah, the quantum aspect, and then then it gets into the quantum versus macro scale, like reconciling all that stuff.
And actually,
Interesting. But
what would the other burning question is there a way to? Okay, so we vacuum energy has all sorts of properties that are being described. String theory has got some really interesting things that it has. Quantum physics has done some really interesting things in trying to illustrate space-time as a connection of vacuum energy entanglement. Very, very interesting things going on. But there's no really agreed upon version. So even in that scenario, it would be like, okay, then what would an expanding universe of that nature look like? Dark energy basically is vacuum energy causing this expansion, according to the lambda CDM theory. But what I'd like to be able to tell, and maybe I missed the opportunity to ask you here is, well, we don't have a measurement of actual vacuum energy currently. We don't have an actual observed measurement.
No, because we can't
actually.
Because we can't actually create temperatures cold enough to create a situation where nothing is moving and still yet be able to observe it. Yeah, we can't.
We have an estimated modified.
Yeah.
We have modified the cosmological constant and given that a value of dark energy. One of the things that's considered the worst experiment at all time is quantum physics predicted a really high vacuum energy, one that we don't think is correct. But it's also like that was just an equation. And then the current thing that's the correct number is also one that's just an equation. This is not based on observation. It would be nice to be able to, if there was some sort of a benchmark, maybe this spinning hydrogen could be something like this, where we could get an observation of vacuum energy, get a quantifiable observation of vacuum energy in the local universe within, and that you'd have to be outside of the galaxy, just outside the Milky Way, and back through time, further back to see, because if that's dynamic, if that vacuum energy is in any way dynamic between gravitationally bound objects, it might give us a different spin on expansion, or different definition of that expansion. Because if it's the driver, that's the dark energy. That would be basically what dark energy is equivalently a vacuum energy, but we don't know what exactly it's made of or what its energy level is. We just see a fact. Anyway, I will go. I got to go start a day.
I know.
I will see.
Now I'm reading another article by Ethan. Okay, here's another one from Big Think that he wrote. I'm putting it in the chat again. And talking about whether or not the universe, when it's expanding, is it stretching? Is it creating space? What's happening? So he goes into, there's some really neat images and other things.
Some cool stuff, but it's, I think the conclusion without reading it is like, we don't know. Like there's a lot of work you got to do if you're now creating space, because space-time.
But there's a lot of, we don't know, but we can talk about what I think I like about what Ethan does is he talks about what we do know. And he's like, and also, but this is how we got here. Like, he's like, and this is where we started thinking about it. And this is,
No, but my point is the stretching space versus the creating space is debated. Like they don't know. Is there an infill? Is space generative? Space-time generating new space-time? And if so, what is the mechanism by which it is doing it homogeneously and constantly everywhere in the universe at the same time?
Yeah. This is a great quote from his article. You see, space itself is not something that's directly measurable. It's not like we can go out and take some space and just perform an experiment on it.
Yeah, it's a problem. It's a problem.
Yeah. I mean, everything is inference, right? We can do experiments and then see what results. And then we have to kind of go, okay, let's step backwards logically from here and infer what might be causing those results.
Yeah, and so we use light. And light is the thing we use because nothing can move faster than the speed of light. Well, almost. Almost. It's speed of light in a vacuum. But then even then, almost. Because there is something that moves as fast as, if not faster than, the speed of light in a vacuum, which is gravity.
It still takes time for gravity to propagate. But gravity isn't a particle. I don't think gravity is a particle.
It's ripples in space-time. It's ripples in it. But the point is that gravity, unaffected by any matter, is always operating at that speed of light maximum. Right? Light has everything else that can get in the way of light gets in the way of light. Light itself doesn't slow down, but its energy can change, and it can not get from point A to point B. It's the same point. It's the same speed as gravity wave. When we captured our gravity wave from LIGO, gamma rays showed up a second and a half later. Gravity wave wins. Gravity wave unimpeded is going to win. Now that could be because the gamma rays were released slightly after the gravity wave took off, and there's all sorts of explanations. But this is Einstein's point in saying that, if the light from the sun, or the sun just poofed out of existence, it would still be 8 minutes before our orbit would change, because gravity propagates through space-time, speed of light. Okay. That means it's a property of space-time, the speed of light. Not the speed of light. You could take the same equation of E equals mc squared, and you could get rid of c squared, and you could say energy equals mass times a volume of space-time. And you're saying the same thing, which means that there's a carrying capacity for space-time. This is very much ether theory. This is why Einstein was very careful to step away from calling it ether theory. like tired light and like a lot of these things that don't have evidence, there were 19 different ether theories before Einstein came along. He rebranded it space-time, gave it a geometry, and already before him, there was geometry was being formed, and all the mechanical aspects of an ether theory, things like friction and energy loss, all these things had already been removed by research, by theoretical physicists. It had already been working on models that removed all the mechanical properties that ether had. So he calls it space-time, but in 1920 speech, he's very clear, giving the props to ether theory that he can't imagine time working or space-time or gravity operating without an ether, without an underpinning conduit of some sort for energy to move in. There's more to do, and I preface all of this as saying, as long as your crackpot physics theory agrees with Einstein, I feel like you're in good company. And Einstein did believe that space-time was finite, and his equations did show that it could be contracting or expanding. But it didn't say which direction. It doesn't have a force connected to gravity. So the graviton, this is the attempts that quantum physics has tried to make to add gravity as a force have all failed.
Yep.
Things that are adding extra dimensions, while useful in creating a model, have done nothing to explain the actual world. If you stick with Einstein, you do end up with a modern ether theory. But then it also brings up some really interesting questions when you're talking about things like whether the universe is expanding or contracting. If you're relying on redshift, I think you make some presumptions about. You have to make a lot of assumptions about what is affecting that redshifting. What is causing that redshifting?
Yeah. So the end of the article that's more recent about this stretching or creating space, he's basically saying what you're saying here. All of the radiation within our universe, including every gravitational wave, behaves as though space is stretching, although space itself isn't getting any thinner. The dark energy within our universe behaves as though new space is getting created, although there's nothing we can measure to detect this creation. General relativity is the only thing that can tell us how space behaves, evolves, and affects the energy within it, but it can't tell us what space is. So we have to just kind of go with this and not add a whole bunch of stuff to it. Space neither stretches nor gets created, but as simply as Einstein's theory describes it. We can learn the how, even if we can't get the what yet.
And that's why, I have no idea of knowing if any of it's correct, but that's why I like the concept of space-time contracting, because it doesn't create new space since the Big Bang.
Yeah.
It more condenses it, sort of. It gathers it back up of like a shrinking.
Then we're going to have a big crunch.
Well,
it's not
maybe
accelerating. If you're having it contracting, then that means that it's decelerating. It's contracting.
Yeah. But
it's all math, everybody.
It would be separate from the mass, which means you would be infilling as this space-time contracts down. You'd be infilling. It's space-time. It doesn't care if there's if you can stretch it, then you can fit more of it in between two gravitationally bound objects.
I wonder if you do deflate the universe balloon, does it end up with those weird wrinkles on it, like a balloon that's been deflated? You know how you stretch a balloon and it gets all big, and you deflate it, and then it's like, oh, the surface is all wibbly wobbly.
Yeah, and what's weird is that whatever that outer area is, as space-time contracts, would be radiating in, because it would be, as it is actually coming into contact, the edge of space-time meets matter as it goes in. You would expect there to be energy that's now can no longer move in that direction. It can no longer expand out of the bubble. It's there, and the only way it can move is back in again. So you would expect to get an imprint of the early universe on the interior of the bubble, of the interior of the balloon, would be able to tell you.
Yeah, if there was a balloon interior. But
if it's finite, which this is the closed versus the open universe kind of a thing.
Yeah,
Again, sticking with Einstein, finite amount of space-time. It's finite. Otherwise, rules of gravity.
The question is, at the quantum scale, right? Can we go back and determine the structure of the modern universe, or predict the structure of the early universe as it started to congeal as the plasma became bits and pieces and particles and turned into stuff, and became heterogeneous.
Also, it's all
Right?
it's all space-time. Even the matter.
I know. That's what I said last week. It's all. The reason that the dark energy never changes is because that's all there is. It's all energy. It's all
and the dark energy could be changing. Like, that would be another thing that would be actually a prediction of a contracting space-time.
But that's the thing, because it's expanding. What Ethan was saying in the article that I was looking at was that even as it's expanding, space gets stretched, time gets stretched, dark energy stays the same. It doesn't change. The density doesn't change. So if it's expanding and the density doesn't change, if it contracts, the densities shouldn't change either. But that means that there is an addition or a loss, right?
So here's the thing. That's probably not true.
I know.
That is a constant that has been set in there and been used. But the prediction I would say that my contracting space-time would make, if we make a prediction, is that that dark energy is dynamic, that it does change over time. Whether the universe is expanding or contracting, it will be doing so uniformly and homogeneously, because it will be a density of space-time, or a quantized density, at least, as it contracts or expands. And you wouldn't be contracting space-time and then diluting void energy, because you've also added more void energy between you and other things. But it would mean that it was dynamic in the sense that it would, well, maybe it wouldn't be dynamic. I think actually it would have to be more dynamic, maybe, if it was expanding. Because then you're stretching out. Then you're taking distance and actually saying distance is longer and time is different, which is the only way you measure time. Time isn't. It is an emergent quality. It's not actually a quality of space-time. It is the thing that it's an emergent quality of energy moving through space-time. Otherwise, if you just had a big bubble of space-time, there is no such thing as time at that point, because there's nothing. If it's nothing moving through it,
right? Exactly. Time is a function of change.
But you should see a shrinking space-time having a somewhat dynamic effect on that measurable dark matter or dark energy combined. You should see some differences in the way that the universe behaves. Not different physics, nothing like this. I don't know. Maybe not. Don't know.
I
You don't have
wanna
a measurement
see
of dark energy. You don't even have any place to start with.
I know. I want to see experiments that manipulate dark energy. That's what I want to see. That'd be
Oh, I
great.
guess you could have it wouldn't be dynamic dark energy. It would be dynamic dark matter, because if that clumping is gravity without matter.
Yeah.
Forget that there's matter. You want to make matter responsible for dark matter, that's fine. But right now, currently, we don't have a matter attached.
You're just
to it. What we have
saying
is
no
gravity.
matter, but there might be matter. But there
could be matter, but you're
there's
guessing.
mass.
There's gravity. There's space time.
Gravity.
There is space time stretching.
Mm-hmm.
That's what we have seen. We have seen gravity. We have not seen matter.
No, I know. That's yes, right.
Right.
But yeah, we've seen the
gravity
impact of the stretching or the distortion of space-time, from which we infer gravity, from which we infer mass.
Right.
Yeah. Infer. It's all inference.
But gravity is not a property of mass. It's a property of space-time.
Yes. It's an emergent property.
Yeah. So it's both. It takes both so far. But that's why they think it's dark matter is dark matter, not just free floating gravity. A little extra space-time. Got a little extra space-time over here. A little too much over there.
Hey, you got a little space-time stuck in your teeth.
Yeah. A little space-time stuck in there. That's fine.
That's where the cavities come from. Ow. Oh, I'm in trouble.
Yeah,
I need to go to bed.
Condensing space-time would either dilute or concentrate. Dilute or do nothing to vacuum energy. But if we're looking over great distances, how do we tell distance? Through light. And how does light travel? Medium or geography. If you don't like conduit space, if you don't like the idea of an ether, then it's traveling through geometries of what? Huh? How? Yeah. Anyway. Gotta go. I should have gone a little while ago. I gotta go. I will see you next week. You are muted. You're completely muted. I can't hear anything.
Well, I said I need to go to bed, and all of a sudden you're the one panicking, and I'm like, why are you panicking? I just said I need to go to bed.
That. You were on the
Apparently muted myself.
Everybody look under your bed. Make sure there's no lions. Good night.
Don't get eaten by the man-eating lions of Savo. All right, everybody. Thank you for joining us. Come back again next week. We'll talk about more fun stuff. Say good morning, Justin.
Good morning, Justin. Say good night, Kiki.
Good night, Kiki. All right, everybody. Stay safe, stay healthy, stay curious, and stay lucky. Ending